Have you ever noticed that absolutely nothing in the universe is truly at rest? Not a single atom, not a grain of dust, not even the space between the stars. Right now, as you sit quietly, your atoms vibrate 10 trillion times per second. The blood in your veins flows at 30 centimetres per second. Your heart beats 60 to 100 times per minute. And beneath it all, you're hurtling through space on a planet spinning at 1,000 miles per hour, orbiting a star at 7,000 miles per hour, while racing through the galaxy at nearly 500,000 miles per hour. But there's something deeper than all this motion, something that makes stillness impossible in our universe. It's written into the very fabric of reality itself, encoded in the laws that govern everything from the smallest quantum particle to the largest galactic cluster. Tonight, we'll uncover the hidden force that ensures nothing can ever truly stop moving, why even empty space refuses to be still, and how this cosmic restlessness might be the reason you exist at all. So close your eyes, feel the gentle motion of your breath, and follow me into the universe where stillness is the only thing that cannot be. If this quiet journey into motion and mystery speaks to your wandering mind, a soft like or gentle subscribe would fill my heart with gratitude. Your support becomes part of this endless dance of stories, helping these cosmic whispers reach other curious souls drifting through the night. In 1927, a young German physicist named Werner Heisenberg made a discovery that would forever change our understanding of reality itself. He was working late in his laboratory, struggling with the mathematics of quantum mechanics, when he stumbled upon something extraordinary. The equations were telling him that the universe has a built-in limit to how precisely we can know certain things about particles. This wasn't a limitation of our measuring instruments or our techniques, but a fundamental property woven into the fabric of existence itself. Heisenberg's uncertainty principle revealed that there is an irreducible restlessness at the heart of everything, a cosmic rule that makes perfect stillness impossible. The mathematical relationship he discovered can be written as delta x times delta p is greater than or equal to h bar divided by 2, where delta x represents the uncertainty in position, delta p represents the uncertainty in momentum, and h bar is Planck's constant divided by 4 pi. This tiny number, approximately 1.05 times 10 to the negative 34 joule seconds, might seem insignificant, but it governs the entire universe. What this equation tells us is profoundly unsettling to our everyday intuition. If you know exactly where a particle is, you cannot know how fast it's moving. If you know exactly how fast it's moving, you cannot know where it is. The more precisely you try to pin down one property, the more uncertain the other becomes. This isn't just a statement about measurement, it's a statement about reality itself. Heisenberg reflected on this principle throughout his life, eventually writing that any use of the words position and velocity with accuracy exceeding that given by his relation is just as meaningless as the use of words whose sense is not defined. Think about what this means for the atoms in your body right now. Every single one of them is subject to this fundamental uncertainty. Their electrons cannot be perfectly still because perfect stillness would require yet knowing both their exact position and their exact momentum simultaneously, which the universe forbids. So they dance, constantly and eternally, in a quantum ballet that has been going on since the moment of their creation. This discovery sent shockwaves through the scientific community because it challenged the very foundation of classical physics. Isaac Newton's universe was one of perfect predictability, where if you knew the position and velocity of every particle in the universe, you could predict the future with absolute certainty. Heisenberg's principle shattered this dream of complete knowledge. The universe, it turns out, is fundamentally uncertain, fundamentally restless. But this uncertainty isn't chaos. It's a different kind of order. It's an order that embraces motion as its core principle. The uncertainty principle doesn't just apply to position and momentum, it extends to energy and time as well. The more precisely you try to measure the energy of a quantum system, the less precisely you can determine when that measurement was made. This energy-time uncertainty has profound consequences for what we call empty space. According to quantum field theory, even the vacuum of space is subject to these uncertainty relations. Virtual particles carrying energy borrowed from the quantum vacuum can pop into existence for brief moments before disappearing again. The more energy they borrow, the shorter the time they can exist. This creates a seething foam of activity at the smallest scales, a constant bubbling of creation and annihilation that ensures even empty space is never truly empty or still. The philosophical implications of Heisenberg's discovery are staggering. It means that nature herself has chosen motion over stillness as her fundamental state. The universe isn't just moving because things happen to be set in motion at the Big Bang. Motion is written into the laws of physics themselves. Stillness isn't just rare or difficult to achieve, it's actually impossible. When Heisenberg first presented his findings, many physicists resisted the idea. Albert Einstein famously declared that God does not play dice with the universe, expressing his discomfort with the probabilistic nature of quantum mechanics. But decades of experiments have confirmed Heisenberg's insight over and over again. Every test of quantum mechanics, from the behavior of electrons in atoms to the operation of lasers and computer chips, confirms that uncertainty and motion are built into the very foundation of reality. The uncertainty principle also explains why atoms don't collapse. In classical physics, the negatively charged electron should spiral into the positively charged nucleus, radiating energy as it accelerates inward. But quantum mechanics forbids this because it would require the electron to have both a definite position within the nucleus and zero momentum. The uncertainty principle prevents this collapse by ensuring that confining an electron to a smaller space increases its momentum uncertainty, giving it enough kinetic energy to resist the electrical attraction of the nucleus. In this way, the uncertainty principle doesn't just prevent perfect stillness, it prevents the collapse of matter itself. Every chemical bond, every molecular structure, every living cell exists because the uncertainty principle keeps electrons in constant motion around atomic nuclei. You're not just made of atoms that happen to be moving, you're made of motion itself. Quantum motion that has been flowing uninterrupted since the birth of the universe. Imagine the coldest temperature possible, a state so frigid that it represents the complete absence of heat. This is absolute zero, precisely negative 273 degrees Celsius or zero on the Kelvin scale, a temperature so extreme that it has never been achieved anywhere in the universe, not even in the depths of interstellar space, where temperatures hover shows just a few degrees above this ultimate limit. For centuries, scientists believed that reaching absolute zero would mean achieving perfect stillness, a state where all atomic motion would cease and the universe would finally come to rest. According to classical physics, temperature is simply a measure of how fast atoms and molecules are moving, so it seemed logical that removing all thermal energy would bring everything to a complete stop. This classical expectation painted a picture of absolute zero as the ultimate state of peace, where every particle would settle into perfect motionlessness, like a cosmic symmetry of frozen matter. But quantum mechanics revealed a shocking truth that overturned this intuitive understanding completely. Even at absolute zero, motion persists in a form so fundamental that it cannot be eliminated by any cooling process, no matter how perfect or prolonged. This irreducible motion is called zero-point energy, and it represents the minimum amount of energy that any quantum system must possess, even when stripped of every possible bit of thermal energy. The mathematical expression for this mysterious energy is beautifully simple yet profound in its implications. 0-point energy equals 1/2 times Planck's constant times the frequency of the system, written as E0 equals 1/2 h bar omega. This equation tells us that every oscillating system in the universe, from the smallest atomic vibration to the quantum fields that permeate all of space, must retain a minimum amount of energy even when cool, to the ultimate limit. Planck's constant, that tiny number we encountered before, once again governs this fundamental limit, ensuring that the universe can never achieve perfect stillness. The physical reality of 0-point energy becomes apparent when we consider what happens to matter as we approach absolute zero. In the classical world, we would expect all substances to solidify as thermal motion decreases, with atoms settling into rigid crystalline structures held together by chemical bonds. Most substances do indeed behave this way, transitioning from gas to liquid to solid as temperature drops, but helium, the second lightest element in the universe, defies this expectation in a spectacular way. No matter how close to absolute zero you cool liquid helium under normal atmospheric pressure, it stubbornly reuses to freeze into a solid. The reason for this bizarre behaviour lies in the delicate balance between the weak forces that try to hold helium atoms together and the vigorous 0-point motion that keeps them dancing apart. Helium atoms are so light and the forces between them so weak that zero-point energy alone provides enough motion to prevent crystallization. Even at temperatures just thousandths of a degree above absolute zero, helium atoms continue their quantum dance, sliding past each other in a frictionless liquid state that defies our everyday understanding of matter. This superfluid helium exhibits properties that seem almost magical, flowing without resistance and climbing up the walls of containers in apparent defiance of gravity. These extraordinary behaviours are direct manifestations of quantum motion persisting at the lowest possible temperatures, visible proof that the universe refuses to be perfectly still. The implications of zero-point energy extend far beyond exotic laboratory experiments with liquid helium. Every atom in your body, every molecule in the air around you, every particle in the most distant galaxies possesses this irreducible quantum motion. The carbon atoms that form the backbone of your DNA are vibrating with zero-point energy. The oxygen molecules you breathe are jiggling with quantum motion that cannot be stilled, and the electrons that carry signals through your nervous system dance their eternal dance around atomic nuclei with energy borrowed from the quantum vacuum itself. Even in the emptiest regions of space, where matter is so sparse that cubic meters might contain only a few scattered atoms, zero-point energy ensures constant activity. The quantum fields that permeate all of space undergo perpetual fluctuations driven by zero-point energy. These fluctuations are not mere mathematical abstractions, but real physical phenomena with measurable consequences. Virtual particles, fleeting manifestations of these quantum field fluctuations, constantly pop into existence and disappear again throughout the universe. These virtual particles exist for such brief moments that they seem to violate conservation of energy, borrowing energy from the quantum vacuum and paying it back so quickly that the universe's accounting system never notices the debt. The Heisenberg uncertainty principle permits these temporary energy loans because the more energy borrowed, the shorter the time it can be kept, maintaining the overall balance of the cosmic ledger. Electron-positron pairs appear and annihilate, photons flash into existence and vanish, quarks and antiquarks dance briefly in the quantum foam before returning to nothingness. This constant creation and destruction driven by zero-point energy means that what we call empty space is actually a seething cauldron of activity, a quantum soup of virtual particles engaged in an eternal ballet of existence and non-existence. Zero-point energy reveals that the universe has chosen motion as its ground state, its default condition, its natural mode of existence. Even when all removable energy has been extracted, when all heat has been drained away, when matter has been cooled to the theoretical limit of cold, quantum motion persists as an irreducible reminder that stillness is an illusion. The greatest misconception in human history might be our notion of empty space. When you look up at the night sky and see the vast darkness between stars, when you imagine the void between atoms, when you picture the ultimate emptiness that you think would remain if every particle of matter and every photon of light were somehow removed from a region of space, you are envisioning something that simply does not exist. What we call empty space, what physicists term the quantum vacuum, is not empty at all, but rather a seething ocean of fluctuations, a dynamic arena where the fundamental fields of nature engage in an eternal dance of creation and destruction that makes the most violent storm seem peaceful by comparison. This revelation emerged from quantum field theory, the marriage of quantum mechanics and special relativity that describes how particles and forces behave at the smallest scales. According to this theory, every point in space is filled with quantum fields for every type of particle that exists. Electromagnetic fields, electron fields, quark fields, neutrino fields, and more. These fields permeate all of space uniformly, and they cannot be turned off or removed any more than you could remove the concept of temperature from a region of space. Even when no real particles are present, these fields continue to fluctuate according to the uncertainty principle, creating what physicists call virtual particles that flash into existence and vanish again in time so brief that they challenge our very conception of existence itself. These virtual particle pairs appear and disappear in approximately 10 to the negative 23 seconds, a time span so short that if you scaled it up to the duration of a human heartbeat, a single heartbeat would last longer than the current age of the universe. During their fleeting existence, these virtual particles borrow energy from the quantum vacuum in an amount determined by the uncertainty principle. The more energy they borrow, the shorter their permitted existence, creating a cosmic system of perfectly balanced books where every energy loan is repaid with mathematical precision. Electron and positron pairs materialize and annihilate, photons appear and disappear, quarks and antiquarks dance briefly before returning to the void, all part of an intricate choreography that ensures the vacuum is never truly vacant. The reality of these quantum vacuum fluctuations was dramatically confirmed in 1948 when Dutch physicist Hendrik Casimir predicted a remarkable effect that would make the invisible visible and the theoretical measurable. He calculated that if two uncharged metal plates were placed very close together in a vacuum, the quantum fluctuations of space itself would create a tiny but measurable force pushing the plates together. This happens because the space between the plates can only accommodate electromagnetic fluctuations with wavelengths that fit exactly between the plates, while the space outside can accommodate fluctuations of any wavelength. This creates an imbalance in the quantum pressure, with fewer virtual photons pushing outward from between the plates than pushing inward from outside, resulting in a net attractive force. When the Casimir effect was finally measured experimentally decades later, it matched theoretical predictions with extraordinary precision, providing irrefutable proof that empty space is filled with real, measurable activity. The Casimir force is incredibly weak, roughly equivalent to the weight of a red blood cell pressing down on an area the size of a fingernail, but it is real and measurable with modern instruments. Engineers designing microscopic devices must now account for the Casimir effect, as it can cause moving parts to stick together in microelectromechanical systems. The energy contained in the quantum vacuum is staggering beyond human comprehension. When physicists attempt to calculate the energy density of quantum vacuum fluctuations, they find numbers so large they seem to mock our understanding of reality. Conservative estimates suggest that every cubic centimetre of empty space contains enough virtual particle activity to power the entire world for billions of years. More extreme calculations yield energy densities that exceed the total energy content of all the matter and radiation in the observable universe by factors of 10 to the power of 120, a number so vast that it has more zeros than there are atoms in the visible cosmos. This enormous energy density presents one of the deepest puzzles in modern physics, known as the cosmological constant problem. If the quantum vacuum really contains this much energy, it should curve spacetime so dramatically that the universe would either collapse instantly or expand so rapidly that no structure could ever form. The fact that we exist in a universe with relatively gentle expansion suggests either that our calculations are wrong or that some unknown mechanism cancels out most of the vacuum energy. Despite this theoretical confusion, the energy clearly exists in some form because we can measure its effects through phenomena like the Casimir force. The quantum vacuum energy cannot be extracted for practical use, making perpetual motion machines forever impossible. This might seem counterintuitive given the enormous energy supposedly available in every cubic centimetre of space, but the zero-point energy of the vacuum represents the ground state of the universe itself. You cannot extract energy from a system that is already at its lowest possible energy state any more than you could dig a hole deeper than the bottom of the ocean. Every point in space contains quantum harmonic oscillators corresponding to all possible modes of oscillation for all quantum fields. These oscillators can never be completely stilled because that would violate the uncertainty principle. The sum of all these contributions yields the enormous vacuum energy density that puzzles physicists, but also ensures that space itself can never be truly empty or still. When you touch a hot stove and immediately pull your hand away, you're directly experiencing the most fundamental truth about matter. Heat is motion. Every sensation of warmth or cold, every degree measured by a thermometer, every calorie of energy that powers your body represents the ceaseless dance of atoms and molecules in perpetual motion. This revelation emerged in the 19th century as scientists developed what we now call kinetic theory, a revolutionary understanding that transformed our conception of matter from static building blocks into dynamic entities engaged in eternal choreography. Temperature, which seems like such a simple concept in everyday life, is actually a measure of the average kinetic energy of the atoms and molecules that make up any substance. When something feels hot, it means its atoms are moving rapidly. When something feels cold, its atoms are moving more slowly. But crucially, they are always moving, always vibrating, always jiggling with an energy that comes from the thermal environment around them. The mathematical relationship that governs this motion is elegantly simple. The average kinetic energy of an atom or molecule equals 1/2 times the Boltzmann constant times the absolute temperature. This equation, written as 1/2 kg sub B times T, contains within it the secret of why matter behaves as it does, why gases expand when heated, why liquids flow, and why solids maintain their shape while still allowing their constituent atoms to vibrate ceaselessly around equilibrium positions. The Boltzmann constant, named after Austrian physicist Ludwig Boltzmann, who helped establish kinetic theory, serves as a bridge between the microscopic world of individual atoms and the macroscopic world of temperature that we experience directly. Its value, approximately 1.38 times 10 to the negative 23rd joules per Kelvin, might seem incredibly small, but when multiplied by the enormous number of atoms in any macroscopic object, it determines all the thermal properties we observe. At room temperature, roughly 300 Kelvin or about 27 degrees Celsius, this equation tells us that atoms possess an average kinetic energy of about 4.1 times 10 to the negative 21 joules each. While this energy seems minuscule, when we consider that a single gram of matter contains approximately 10 to the 23rd atoms, the total kinetic energy becomes enormous, enough to power human civilization for millions of years if it could somehow be harnessed efficiently. Right now, as you sit reading or listening to these words, the atoms in your body are moving at speeds that would astound you if you could observe them directly. The carbon atoms that form the backbone of your DNA are vibrating and rotating at average speeds of about 500 meters per second, faster than the speed of sound in air. The oxygen molecules flowing through your bloodstream are tumbling and spinning as they travel at similar velocities, colliding with each other millions of times per second. The calcium atoms in your bones, the iron atoms in your blood, the sodium and potassium atoms that enable your nerves to fire, all are engaged in constant thermal motion that never ceases, not even during the deepest sleep. Your brain itself operates through processes that depend fundamentally on this atomic motion, as neurotransmitter molecules diffuse across synapses through random thermal motion. Electrical signals propagate along nerve fibers through the motion of ions, and proteins change shape through thermal fluctuations that enable them to perform their biological functions. Yet despite this incredible atomic activity occurring within your body at every moment, you feel none of it directly. The reason for this apparent paradox lies in the statistical nature of thermal motion and the enormous numbers involved. While individual atoms move at hundreds of meters per second, they travel only nanometers before colliding with neighbouring atoms, changing direction in a completely random way. This creates a situation where, although every atom is moving rapidly, the net motion of any macroscopic region averages to essentially zero. It's like being in a room filled with millions of people all walking rapidly in random directions. While each person moves quickly, the crowd as a whole doesn't go anywhere, and you, standing among them, don't experience any net force pushing you in any particular direction. This statistical cancellation of individual atomic motions allows macroscopic objects to appear stable and motionless, while being composed of frantically active microscopic constituents. The connection between heat and motion runs so deep that heat simply cannot exist without motion. When you rub your hands together to warm them, you are converting the organized motion of your muscles into the disorganized thermal motion of atoms in your skin. When an electric heater warms a room, it converts electrical energy into the kinetic energy of air molecules, which then collide with objects in the room, transferring their motion and creating the sensation of warmth. When the sun heats the Earth, electromagnetic radiation from nuclear fusion in the solar core excites atmospheric molecules into more vigorous motion, driving weather patterns and enabling life to flourish. In every case, heat represents energy in its most disordered form, the random kinetic energy of atoms and molecules that have been set into motion by various physical processes. Modern technology exploits thermal motion in countless ways, from the operation of heat engines that convert thermal energy into mechanical work to the design of materials with specific thermal properties for specialized applications. Understanding atomic motion is crucial for developing new materials with tailored properties, as scientists can now design substances with specific thermal conductivities, heat capacities, and thermal expansion coefficients by controlling the ways in which atoms move within crystalline or amorphous structures. In 1827, a Scottish botanist named Robert Brown was examining pollen grains suspended in water under a microscope when he observed something that would fundamentally change our understanding of the invisible world around us. The tiny grains, each about 1,000th of a millimetre across, were engaged in a peculiar dance, jiggling and jumping in seemingly random directions with no apparent cause. Brown initially thought this motion might be evidence of some vital force within the pollen, some spark of life that animated these reproductive structures even when removed from their parent plants. But when he repeated his observations with particles of glass, dust, and other clearly inanimate materials, he found the same mysterious motion persisting with undiminished vigour. The particles moved in erratic zigzag paths that defied any simple explanation, sometimes lurching suddenly in one direction, then reversing course and darting off at seemingly random angles, like microscopic dancers performing an intricate choreography without music or conductor. This phenomenon, which became known as Brownian motion in honour of its discoverer, would remain a scientific mystery for nearly 80 years until Albert Einstein provided a brilliant explanation that not only solved the puzzle, but also provided the first direct evidence for the existence of atoms and molecules. Einstein's 1905 paper on Brownian motion, published in the same miraculous year that brought us special relativity and the photoelectric effect, demonstrated with mathematical precision that the erratic motion of suspended particles resulted from constant bombardment by invisible water molecules in random thermal motion. According to Einstein's analysis, the water surrounding each pollen grain or dust particle consists of countless molecules moving at high speeds in completely random directions, colliding with each other and with the suspended particles millions of times per second. While individual molecular collisions are far too weak to move a particle noticeably, the sheer number of impacts creates a statistical imbalance that becomes visible at the microscopic scale. At any given moment, a few more molecules might strike one side of a particle than the other, creating a tiny net force that pushes the particle in a particular direction. An instant later, the random fluctuations might favour a different direction, causing the particle to change course unpredictably. This constant buffeting by molecular impacts creates the characteristic random walk pattern that Brown observed, where particles wander aimlessly through the fluid medium like drunken wanderers taking random steps without any preferred destination. Einstein's mathematical treatment of Brownian motion was remarkably sophisticated, incorporating probability theory and statistical mechanics to predict precisely how suspended particles should behave under molecular bombardment. His equations showed that the mean squared displacement of a Brownian particle should be proportional to time, temperature, and inversely proportional to both particle size and fluid viscosity. Larger particles experience less Brownian motion because they have more mass to resist the random molecular impacts, while smaller particles dance more vigorously because they can be pushed around more easily by the same molecular forces. Higher temperatures increase Brownian motion because warmer fluids contain faster-moving molecules that strike suspended particles with greater energy and frequency. More viscous fluids reduce Brownian motion because the suspended particles encounter greater resistance as they try to move through the thick medium. These relationships allowed Einstein to calculate the exact magnitude of Brownian motion for particles of any given size in any fluid at any temperature, providing testable predictions that could confirm or refute his molecular theory. The experimental verification of Einstein's predictions came through the meticulous work of French physicist Jean Perrin, who spent years making precise measurements of Brownian motion under carefully controlled conditions. Using particles of a uniform size suspended in water, Perrin tracked their positions over time and calculated statistical properties such as average displacement and the distribution of particle positions. His results matched Einstein's theoretical predictions with remarkable accuracy, providing convincing proof that matter really does consist of invisible atoms and molecules in constant thermal motion. Perrin's experiments were so compelling that they converted the last holdouts among scientists who had remained skeptical about atomic theory. Before this work, atoms and molecules were useful theoretical constructs that explained chemical reactions and gas behaviour, but their physical reality remained debatable. Brownian motion provided the first direct observational evidence that these invisible particles actually exist and behave exactly as kinetic theory predicted they should. Modern technology has transformed our ability to observe and manipulate Brownian motion with extraordinary precision. Optical tweezers, which use focused laser beams to trap and manipulate microscopic particles, can now track individual particles undergoing Brownian motion with nanometer precision and millisecond time resolution. These instruments reveal the intimate details of how thermal fluctuations affect particles at different scales, allowing scientists to measure the forces between molecules, study the mechanics of biological motors, and explore the fundamental limits of measurement precision imposed by thermal noise. The dancing dust particles that you can observe in a sunbeam streaming through a window represent the same phenomenon that Robert Brown discovered nearly 2 centuries ago. These particles, typically ranging from a few micrometers down to submicron sizes, are light enough to be visibly affected by collisions with air molecules in random thermal motion. The motion appears more dramatic in bright illumination, not because the light affects the motion itself, but because the scattered light makes the particles visible against the dark background, allowing you to see motion that is occurring constantly but usually invisibly throughout the air around you. Chemical bonds, the invisible forces that hold atoms together into molecules, behave like tiny springs that constantly vibrate with an energy that can never be completely removed, even at absolute zero. These molecular springs oscillate at specific frequencies determined by the masses of the connected atoms and the strength of the bond itself, creating a symphony of motion that permeates every substance in the universe. Infrared spectroscopy reveals this hidden world of molecular vibration by detecting the characteristic frequencies at which different bonds oscillate, allowing scientists to identify unknown compounds and study molecular structure through the unique fingerprint of vibrational motion that each molecule possesses. When infrared light strikes a molecule, bonds that vibrate at the same frequency as the incoming radiation absorb energy and begin oscillating more vigorously, creating absorption peaks that appear as dips in the transmitted light spectrum. This technique has revolutionized chemistry by making molecular motion directly observable, showing that every chemical bond is in constant motion, stretching and compressing like a microscopic spring thousands of times per second. Zero-point motion fundamentally affects molecular structure in ways that would be impossible in a classical world without quantum mechanics. Without this irreducible quantum vibration, chemical bonds would be shorter and stronger, molecules would be more compact, and the familiar chemistry that enables life would work completely differently. The bond lengths we measure in real molecules are averages over the constant vibrational motion, with atoms spending their time oscillating around equilibrium positions rather than sitting motionless at fixed distances. Water molecules, for example, owe their bent shape partly to zero-point motion that keeps the hydrogen atoms vibrating around their average positions, creating the molecular geometry that gives water its unique properties as a solvent and enables it to form the hydrogen bonds essential for life. Protein folding, one of the most remarkable processes in biology, depends critically on thermal fluctuations and molecular motion to enable these complex molecules to find their proper three-dimensional shapes. As a newly synthesized protein chain emerges from a ribosome, it begins as a linear sequence of amino acids that must fold into a precise configuration to become functional. This folding process relies on thermal motion to allow different parts of the protein to sample various conformations, gradually settling into the lowest energy state through a process guided by the chemical properties of the amino acid sequence. Without thermal fluctuations, proteins would become trapped in incorrect configurations and could never reach their native folded states. Molecular chaperones assist this process by providing controlled environments where thermal motion can work efficiently without allowing proteins to aggregate improperly. The constant vibration of chemical bonds also enables conformational changes that are essential for protein function, allowing enzymes to change shape when they bind substrates, enabling transport proteins to open and close channels through cell membranes, and permitting regulatory proteins to switch between active and inactive states in response to cellular signals. Life itself represents an extraordinary example of organized motion at the molecular scale, with every biochemical reaction depending on thermal motion to bring reactant molecules together with sufficient energy to overcome activation barriers. Enzyme catalysis works by lowering these energy barriers and properly orienting reactive molecules, but the actual reaction still requires thermal motion to provide the kinetic energy needed for chemical transformation. Metabolic pathways consist of carefully orchestrated sequences of molecular collisions and conformational changes, all powered by the random thermal motion of molecules in the warm, aqueous environment of living cells. DNA replication depends on thermal motion to separate the double helix strands and allow DNA polymerase enzymes to access the template, while transcription relies on thermal fluctuations to enable RNA polymerase to move along DNA and create messenger RNA molecules. Even the genetic code itself is read through molecular motion, as transfer RNA molecules diffuse through the cytoplasm and bind to ribosomes through thermally driven collisions that eventually result in protein synthesis. The signal transduction pathways that allow cells to respond to their environment operate through cascades of molecular motion, with signaling molecules diffusing through cellular compartments, binding to receptor proteins that change shape in response, and triggering conformational changes that propagate information throughout the cell. Membrane transport processes rely on thermal motion to drive the diffusion of ions and small molecules across cellular boundaries, while larger molecules are moved through active transport mechanisms that harness the energy of molecular motion to pump substances against concentration gradients. The constant jiggling of molecules in biological membranes maintains the fluid properties necessary for cellular function, allowing membrane proteins to move and rotate within the lipid bilayer while maintaining the selective permeability that defines cellular boundaries. Even the process of evolution depends on molecular motion, as thermal fluctuations cause occasional errors in DNA replication and repair, creating the genetic variations that natural selection acts upon over time. Modern pharmaceutical research exploits our understanding of molecular motion to design drugs that bind to specific target proteins through carefully engineered molecular interactions. Computer simulations of molecular dynamics allow researchers to predict how drug molecules will behave in the thermal environment of living cells, optimizing their binding affinity and selectivity through rational design principles that account for the constant motion of both the drug and its target. This molecular dance of constant vibration ensures that chemistry remains dynamic and responsive, making possible the complex biochemical networks that sustain life through billions of precisely coordinated molecular interactions occurring every second in every cell. Right now, as you sit quietly reading these words, you're engaged in one of the most spectacular displays of motion in the universe, spinning through space at velocities that would seem impossible if you could perceive them directly. At the equator, Earth's rotation carries you eastward at 1 through 40 miles per hour, or 460 meters per second, faster than the cruising speed of a commercial airliner, completing one full revolution every 3 hours, 56 minutes and 4 seconds. Simultaneously, our entire planet hurtles through its orbit around the Sun at an astounding 7,000 miles per hour, or 30 kilometers per second, covering nearly 600 million miles each year in an elliptical path that brings us slightly closer to our star in January and farther away in July. But Earth's motion is even more complex than simple rotation and revolution, as our planet also wobbles like a spinning top through two additional motions called precession and nutation. Precession causes Earth's rotational axis to trace out a slow circle against the background stars over a period of about 26,000 years, while nutation creates smaller oscillations superimposed on this grand cycle, both effects resulting from gravitational forces exerted by the Moon and Sun on our planet's equatorial bulge. These multiple layers of motion create a cosmic symphony of movement that has persisted for billions of years, yet you feel absolutely none of it because of a fundamental principle that Isaac Newton first articulated in his laws of motion. The key to understanding why we feel motionless despite travelling at such incredible speeds lies in what physicists call uniform motion, the principle that constant velocity motion cannot be detected by any observer moving along with the system. You and everything around you move together through space as a single unit, so there is no relative motion between you and your immediate environment to create any sensation of movement. It's exactly like riding in a smoothly cruising airplane at constant altitude and speed, where you can walk around the cabin, pour a drink, or balance a coin on your tray table without any indication that you're travelling at 500 miles per hour relative to the ground below. Only when the plane accelerates, decelerates, or changes direction do you feel the motion, because acceleration breaks the perfect unity of uniform motion and creates detectable forces. Earth's rotational and orbital motions are so smooth and constant that they create no acceleration forces we can feel, making our high-speed journey through space as imperceptible as the motion of the airplane passenger. The reality of Earth's rotation can be demonstrated through one of the most elegant experiments in physics, the Foucault pendulum, first performed by French physicist Léon Foucault in 1851. This simple device consists of a heavy weight suspended by a long wire or cable, free to swing in any direction while the Earth rotates beneath it. As the pendulum swings back and forth, it maintains its orientation in space while the Earth turns underneath, causing the plane of oscillation to appear to rotate when viewed from the ground. In Paris, where Foucault first demonstrated his pendulum, the plane of swing rotates 11 degrees per hour, completing a full 360-degree rotation in about 32 hours, providing direct visual proof that we live on a spinning planet, even though we cannot feel the rotation. Modern technology depends critically on understanding and compensating for Earth's motion through space, with no system demonstrating this better than the Global Positioning System that provides navigation data to billions of users worldwide. GPS satellites orbit Earth at altitudes of about 2,500 miles, travelling at speeds of roughly 800 miles per hour, while broadcasting precise timing signals that allow receivers to calculate their positions through triangulation. However, the incredible precision required for GPS navigation, accurate to within a few meters anywhere on Earth, means that even tiny relativistic effects caused by motion and gravity must be taken into account. Einstein's special theory of relativity predicts that clocks moving at high speeds run slower than stationary clocks, while his general theory of relativity shows that clocks in weaker gravitational fields run faster than those in stronger fields. GPS satellites experience both effects simultaneously. Their high orbital speeds cause their atomic clocks to run about 7 microseconds per day, slower than identical clocks on Earth's surface, while their higher altitude in Earth's weaker gravitational field causes them to run about 45 microseconds per day faster than ground-based clocks. The net effect is that satellite clocks gain about 38 microseconds per day relative to Earth-based time, which would cause GPS positions to drift by about 6 miles per day if left uncorrected. The system must therefore continuously adjust for these relativistic effects, providing constant confirmation that motion through space and time affects the fundamental operation of matter and energy in ways that Einstein predicted over a century ago. Earth's motion through space is not accidental but essential for our survival, as rotation creates the day-night cycle that prevents one side of our planet from becoming scorchingly hot while the other freezes, while orbital motion around the Sun drives the seasonal changes that enable complex ecosystems to flourish. Our planet's motion also generates the magnetic field that protects us from harmful solar radiation, created by the movement of molten iron in Earth's core as our planet spins. Without this motion, Earth would be a lifeless, airless rock like Mars, stripped of its atmosphere by the solar wind and bombarded by deadly cosmic radiation. Our entire solar system, far from being a fixed point in space, races through the Milky Way galaxy at an incredible 490,000 miles per hour, or 20 kilometers per second, carrying all the planets, moons, asteroids, and comets along in a vast spiral trajectory that takes us around the galactic center once every 230 million years. This motion through the galaxy is just one component of a complex hierarchy of movements that governs every object in our cosmic neighborhood, from the fastest orbiting planets to the most distant comets in the Oort cloud. The planets themselves demonstrate a beautiful relationship between distance and speed that follows the fundamental laws of orbital mechanics, with Mercury closest to the Sun racing around its orbit at 47 kilometers per second, while distant Neptune crawls along at just 5.4 kilometers per second, each world moving at precisely the speed required to maintain its stable orbit against the Sun's gravitational pull. These orbital velocities are not arbitrary, but represent a delicate balance between gravitational attraction and centrifugal force, with faster speeds required closer to the Sun where gravitational pull is stronger, and slower speeds sufficient at greater distances where the Sun's influence weakens according to the inverse square law. The entire architecture of planetary motion preserves angular momentum inherited from the original solar nebula that formed our solar system 4.6 billion years ago, when a slowly rotating cloud of gas and dust collapsed under its own gravity while spinning faster and faster like a figure skater pulling in her arms. This conservation of angular momentum explains why all the planets orbit in the same direction and roughly in the same plane, carrying forward the rotational motion of the primordial disk from which they formed through accretion of countless smaller particles and planetesimals. The gravitational interactions between planets create subtle but significant perturbations in their orbits that accumulate over millions of years, causing orbital eccentricities to change, rotational axes to shift, and even entire planets to migrate from their original positions. Jupiter, the solar system's gravitational heavyweight, exerts particularly strong influences on the orbits of other worlds, sometimes acting as a cosmic shepherd that protects the inner planets from asteroid bombardment by deflecting dangerous objects into the outer solar system or ejecting them entirely from the Sun's gravitational embrace. The asteroid belt between Mars and Jupiter contains millions of rocky fragments engaged in complex orbital dances, their paths constantly perturbed by planetary gravity, collisions with other asteroids, and the subtle pressure of solar radiation that can gradually alter orbits over geological time. Some asteroids follow chaotic trajectories that bring them close to Earth, creating the population of near-Earth objects that astronomers carefully monitor for potential impact threats, while others are locked into stable resonances with Jupiter that keep them in predictable orbits for millions of years. Comets represent perhaps the most dramatic examples of solar system motion, following highly elliptical orbits that carry them from the frigid outer reaches of the solar system, where they spend most of their time as dormant balls of ice and rock, to close approaches to the Sun where solar heating vaporizes their surfaces and creates the spectacular tails that make them visible from Earth. The Oort cloud, a spherical shell of comets surrounding the solar system at distances up to 100,000 times farther from the Sun than Earth, contains trillions of these icy wanderers whose orbits can be disrupted by passing stars or galactic tidal forces, ending them on million-year journeys toward the inner solar system, where they become the spectacular visitors we occasionally observe in our night sky. Tidal forces generated by gravitational interactions slowly but inexorably alter the rotational and orbital characteristics of solar system bodies, with the most noticeable effect being the gradual slowing of Earth's rotation caused by the Moon's gravitational pull on our planet's oceans. This tidal friction lengthens Earth's day by about 1.7 milliseconds per century, while simultaneously causing the Moon to spiral slowly away from Earth at a rate of about 3.8 centimetres per year, demonstrating that even apparently stable astronomical relationships are actually dynamic systems in constant evolution. The Sun itself participates in this cosmic motion not only through its journey around the galaxy, but also through its rotation on its axis, once every 25 days at the equator and 35 days at the poles, differential rotation that creates the complex magnetic field patterns responsible for solar flares and the 11-year solar cycle. Even the distribution of matter within the solar system continues to evolve as gravitational interactions redistribute angular momentum between different components, occasionally leading to dramatic events such as the late heavy bombardment that reshaped the inner solar system about 3.9 billion years ago, when orbital resonances among the giant planets destabilized the asteroid belt and sent a barrage of impacts toward the inner worlds. This dynamic nature of solar system motion ensures that our cosmic neighborhood will continue changing over time, with planetary orbits slowly evolving, asteroid populations gradually depleting through collisions and ejections, and new comets periodically arriving from the distant reaches of the Sun's gravitational influence. The remarkable stability that has allowed Earth to maintain conditions suitable for life over billions of years results not from static perfection, but from the dynamic equilibrium of countless gravitational forces that keep our planet in the narrow zone, where liquid water can exist while protecting us from the chaos that characterizes much of the universe beyond our solar system's gravitational embrace. Newton's first law of motion reveals one of the most profound truths about the universe. Objects in motion stay in motion unless acted upon by an external force, a principle that explains why planets don't simply fall into the Sun, despite being constantly pulled by its immense gravitational attraction. The key to understanding planetary motion lies in recognizing that gravity doesn't pull planets directly inward, but rather continuously changes the direction of their motion, bending their paths into closed orbits that balance gravitational attraction with the tendency to travel in straight lines. When a planet moves around the Sun, it's essentially falling toward our star continuously, but it's also moving sideways fast enough that it keeps missing, creating the elegant elliptical trajectories that Johannes Kepler first described in his laws of planetary motion over 4 centuries ago. These elliptical orbits cause planets to vary their speeds dramatically as they travel around the Sun, moving fastest when closest to our star at perihelion and slowest when farthest away at aphelion, a variation that demonstrates one of the most beautiful examples of energy conservation in the natural world. As a planet approaches the Sun, gravitational potential energy converts to kinetic energy, speeding up the world's orbital motion, while the reverse transformation occurs as the planet recedes, slowing its motion but increasing its potential energy in a perfectly balanced exchange that has continued unchanged for billions of years. This constant interconversion between potential and kinetic energy ensures that orbital motion is self-sustaining, requiring no external energy input to maintain the precise velocities needed to keep planets in their stable paths around the Sun. The mathematical elegance of Kepler's laws emerges from the fundamental physics of gravitational attraction, with the inverse square law of gravity creating orbital periods that scale as the 3/2 power of orbital radius, meaning that planets farther from the Sun take disproportionately longer to complete their orbits than simple proportionality would suggest. Binary star systems provide even more spectacular examples of gravitational motion, with two massive stars locked in orbital dances that can last for millions or billions of years, each star following an elliptical path around their common centre of mass, while converting potential energy to kinetic energy and back again in cycles that may take days, years, or centuries to complete. Some binary systems contain stars so close together that they exchange material through gravitational interaction, with hot gas flowing from one star to its companion in streams that spiral inward and heat to millions of degrees, creating some of the most energetic phenomena in the universe. Other binary systems consist of widely separated stars that orbit their mutual centre of mass over periods longer than human civilization has existed, demonstrating that gravitational motion operates on timescales that dwarf human experience while following the same mathematical principles that govern the motion of planets in our solar system. The formation of planetary systems themselves represents one of the most remarkable examples of how motion shapes cosmic structure, beginning with slowly rotating clouds of gas and dust that collapse under their own gravity, while spinning faster and faster due to conservation of angular momentum. As the central region of such a cloud becomes dense enough to ignite nuclear fusion and form a star, the surrounding material flattens into a rotating disk where countless particle collisions gradually organise the chaotic motion into more ordered patterns of circulation around the newborn star. Within these protoplanetary disks, solid particles begin sticking together through gentle collisions enabled by their orbital motion, growing from dust grains to pebbles to boulders to planetesimals, through a process that depends critically on the precise balance between gravitational attraction and orbital velocity. The largest planetesimals eventually become planetary embryos that can gravitationally attract smaller objects, clearing their orbital zones through countless collisions and gravitational encounters that either incorporate debris into growing planets or fling it into different orbits. This process of planetary formation demonstrates how motion at every scale, from the microscopic thermal motion of gas molecules to the macroscopic orbital motion of kilometre-sized objects, contributes to the emergence of the organised structures we observe in mature planetary systems. The gravitational interactions that shape planetary formation continue throughout a system's lifetime, with orbital resonances creating stable configurations that can persist for billions of years, or unstable situations that eventually lead to dramatic changes in planetary orbits. Some planets migrate inwards toward their parent stars due to gravitational interactions with the protoplanetary disk, while others are ejected from their systems entirely through close encounters with more massive worlds, creating the population of rogue planets that wander through interstellar space without any star to orbit. The study of exoplanetary systems has revealed that such orbital evolution is common throughout the galaxy, with many systems showing evidence of past migration events that have left planets in configurations very different from their birthplaces. These discoveries emphasize that gravitational motion is not merely about maintaining stable orbits, but also about the ongoing evolution of planetary systems through complex gravitational interactions that can dramatically reshape the architecture of worlds over cosmic time. The motion of planets, asteroids, comets, and all other objects in gravitational systems represents a fundamental aspect of how the universe organizes itself, creating structure and complexity through the simple but powerful relationship between mass, distance, and the inexorable attraction that keeps everything in motion while preventing gravitational collapse through the precisely balanced dance of orbital mechanics. Our Milky Way galaxy is a vast rotating island of stars, gas and dust that completes one full revolution every 230 million years, carrying our solar system at a speed of 20 kilometers per second through space in a grand orbital dance around the galactic center that has repeated itself about 20 times since Earth first formed. This galactic rotation represents motion on a scale almost impossible to comprehend, with our entire solar system travelling roughly 26 billion kilometers during each circuit around the galaxy, a journey so immense that it has taken us through dramatically different regions of space throughout Earth's history, exposing our planet to varying levels of cosmic radiation and different populations of nearby stars that may have influenced the evolution of life over geological time. The discovery of how galaxies actually rotate, however, revealed one of the greatest mysteries in modern astronomy when astronomer Vera Rubin began measuring the velocities of stars at different distances from galactic centers in the 1970s. According to our understanding of gravity and the distribution of visible matter in galaxies, stars farther from the center should orbit more slowly than those closer in, following the same pattern that governs planetary motion in our solar system, where inner planets like Mercury race around the Sun much faster than outer planets like Neptune. This expectation comes from Kepler's laws applied to galactic scales, where the orbital velocity should decrease with distance as the gravitational influence of the central mass weakens according to the inverse square law, creating what astronomers call a declining rotation curve that drops off rapidly beyond the bright central regions of galaxies. But when Rubin and her colleagues measured the actual velocities of stars using the Doppler shift of their light, they found something completely unexpected. The rotation curves of spiral galaxies remain essentially flat, with stars at the outer edges of galactic disks moving just as fast as those much closer to the center, in direct contradiction to what the visible distribution of matter would predict. This discovery meant that either our understanding of gravity was fundamentally wrong on galactic scales, or there must be enormous amounts of invisible matter providing the additional gravitational force needed to keep these outer stars moving so rapidly without flying off into intergalactic space. The flat rotation curves observed in galaxy after galaxy suggested the presence of what astronomers now call dark matter, an invisible form of matter that makes up roughly 5 times more mass than all the visible stars, gas and dust combined, creating extended halos around galaxies that provide the gravitational scaffolding necessary to explain the observed stellar motions. This dark matter doesn't emit, absorb, or reflect light in any detectable way, making its presence known only through its gravitational effects on the motion of visible matter. But its existence has now been confirmed through multiple independent lines of evidence, including gravitational lensing, galaxy cluster dynamics, and the large-scale structure of the universe itself. The Milky Way exhibits the same flat rotation curve that Rubin discovered in other galaxies, with our own solar system orbiting at approximately the same speed as stars much closer to and much farther from the galactic center, indicating that we too are embedded within a massive dark matter halo that extends far beyond the visible edges of our galaxy. Despite this overall pattern of flat rotation, galaxies also exhibit differential rotation, meaning that different parts of the galactic disk complete their orbits in different amounts of time, with the inner regions rotating faster than the outer regions in terms of angular velocity, even though their linear velocities remain roughly constant. This differential rotation creates and maintains the beautiful spiral arm patterns that characterize galaxies like the Milky Way, as density waves propagate through the galactic disk at different speeds than the stars themselves, creating regions of enhanced star formation where gas clouds are compressed by the gravitational influence of the spiral structure. The spiral arms are not permanent features rotating as solid structures, but rather transient patterns that form and dissolve as different populations of stars move through them at their own orbital velocities, like waves moving through water, while the water molecules themselves follow different paths. Our solar system periodically passes through these spiral arms during its 230 million-year orbit, encountering different densities of gas, dust, and nearby stars that may influence Earth's climate and the rate of cosmic ray bombardment over tens of millions of years. The galactic rotation also creates a phenomenon known as the galactic year or cosmic year, the time required for our solar system to complete one orbit around the Milky Way, during which Earth has experienced dramatic changes in climate, geography, and life forms that span multiple mass extinction and evolutionary radiation events. Since the formation of our solar system 4.6 billion years ago, we have completed approximately 20 galactic years, travelling through different regions of the galaxy that may have exposed Earth to varying amounts of cosmic radiation, different populations of nearby supernovae, and encounters with molecular clouds that could have influenced our planet's climate and atmospheric composition. The study of galactic rotation has also revealed that the Milky Way itself is not an isolated system, but participates in larger-scale motions involving our local group of galaxies, which includes the Andromeda Galaxy approaching us at 110 kilometers per second, for a collision expected in roughly 4.5 billion years. that will dramatically reshape both galaxies and alter the rotation patterns that have persisted for billions of years. Modern observations using space-based telescopes and ground-based surveys are mapping the three-dimensional structure and the motion of stars throughout our galaxy with unprecedented precision, revealing subtle variations in galactic rotation that provide clues about the distribution of dark matter, the history of galactic mergers and interactions, and the complex processes that have shaped our cosmic home over the vast spans of astronomical time. 200 billion stars populate our Milky Way galaxy, each one following its own unique orbital path through space in a vast three-dimensional dance that has continued for over 10 billion years, creating a dynamic stellar ecosystem where individual stellar motions combine to maintain the large-scale structure we observe, while constantly reshaping the galactic environment through gravitational interactions, stellar winds, and the explosive deaths of massive stars. Star formation itself represents one of the most dramatic examples of motion-creating structure, beginning when interstellar gas clouds collapse under their own gravity, while simultaneously spinning faster and faster due to conservation of angular momentum, fragmenting into smaller clumps that eventually become dense enough to ignite nuclear fusion and transform gravitational potential energy into the radiant energy that powers stellar luminosity for millions or billions of years. These stellar nurseries are often triggered by the passage of spiral density waves, compression zones that sweep around the galaxy at different speeds than the stars themselves, creating temporary traffic jams where gas and dust accumulate to densities that are sufficient for gravitational collapse and star formation, then dispersing as the density wave passes and the newly formed stars continue their individual orbital journeys around the galactic center. The spiral arms that give our galaxy its characteristic appearance are not permanent rotating structures, but rather transient patterns maintained by the continuous motion of stars and gas through these density waves, with young, hot blue stars marking the current locations of active star formation, while older, cooler red stars have had time to drift away from their birthplaces and spread throughout the galactic disk. This process creates the illusion of stable spiral structure, even though the individual stars are constantly moving, like the pattern of cars in a traffic jam that persists even as individual vehicles enter and leave the congested region, demonstrating how motion on small scales can create apparent stability on larger scales through purely dynamic processes. Binary star systems, which comprise roughly half of all stars in the galaxy, showcase some of the most complex stellar motions as pairs of stars orbit their common center of mass while simultaneously participating in the galactic rotation, creating intricate three-dimensional trajectories that can persist for billions of years, or lead to dramatic evolutionary outcomes when the stars interact through mass transfer, stellar collisions, or gravitational perturbations from passing objects. Close binary systems often exchange material as stellar winds, and tidal forces strip matter from one star and transfer it to its companion, creating accretion disks of superheated gas that spiral inward while radiating enormous amounts of energy, and occasionally triggering nova explosions when accumulated hydrogen on the surface of a white dwarf star ignites in a thermonuclear blast. Wider binary systems provide natural laboratories for studying gravitational dynamics, with some pairs taking thousands of years to complete a single orbit while maintaining their orbital dance across vast distances that dwarf the size of our solar system, demonstrating the long-range nature of gravitational attraction and the incredible stability that can emerge from purely gravitational interactions over cosmic timescales. Stellar interactions become even more complex in the dense central regions of the galaxy, where the concentration of stars is thousands of times higher than in our local galactic neighborhood, creating an environment where close encounters between stars are relatively common and can dramatically alter stellar orbits through gravitational slingshot effects that accelerate some stars to escape velocities while capturing others into tighter orbits around the supermassive black hole at the galactic center. These gravitational encounters can eject stars from the galaxy entirely, creating a population of hypervelocity stars that race through intergalactic space at speeds of hundreds of kilometers per second, having been accelerated by close encounters with the central black hole or by the disruption of binary systems during their passage through the galactic core. Stellar collisions, while extremely rare in the outer regions of galaxies like our own, become more probable in dense stellar environments such as globular clusters and galactic centers, where the collision of two stars can create exotic objects such as blue stragglers that appear younger than their surroundings, or trigger the formation of massive stars through the merger of smaller stellar components. The motion of stars within the galaxy also redistributes chemical elements throughout the galactic disk as stellar winds and supernova explosions disperse the products of nuclear fusion into the interstellar medium, enriching the gas from which future generations of stars will form and gradually increasing the metallicity of the galactic disk over cosmic time through this ongoing process of stellar nucleosynthesis and chemical mixing driven by stellar motions. Even our own Sun participates in this grand choreography, oscillating up and down through the galactic plane every 64 million years while maintaining its roughly circular orbit around the galactic centre, periodically passing through regions of higher and lower stellar density that may influence the rate of cosmic ray bombardment and the frequency of nearby supernova explosions that could affect Earth's climate and atmospheric chemistry over geological timescales. The cumulative effect of all these individual stellar motions creates phenomena such as stellar streams, coherent groups of stars that share similar velocities and chemical compositions, marking the disrupted remnants of globular clusters or small galaxies that have been torn apart by tidal forces during their orbital motion through the Milky Way, leaving behind trails of stars that serve as fossil evidence for past gravitational interactions and galactic mergers that have shaped our galaxy's current structure and stellar population. Our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companion galaxies, moves through space as a gravitationally bound unit toward the Virgo cluster at an impressive 600 kilometers per second, demonstrating that even entire galaxy clusters participate in vast motions that dwarf the already incredible velocities of individual stars and planetary systems. This motion toward Virgo represents just one component of an even grander pattern of cosmic flow driven by a mysterious gravitational anomaly called the Great Attractor, a massive concentration of matter located roughly 250 million light-years away that exerts such powerful gravitational influence that it affects the motion of galaxy clusters across hundreds of millions of light-years, pulling thousands of galaxies toward itself through gravitational forces that operate on the largest scales in the observable universe. The Great Attractor itself appears to be part of an even larger structure called the Shapley supercluster, demonstrating that gravitational motion organizes matter into hierarchical patterns where individual galaxies cluster into groups, groups merge into clusters, clusters aggregate into superclusters, and superclusters flow along vast filaments that form the cosmic web spanning billions of light-years across the observable universe. Galaxy mergers represent some of the most spectacular examples of large-scale gravitational motion. As entire stellar systems containing hundreds of billions of stars approach each other over millions of years, their mutual gravitational attraction gradually overcoming the expansion of space itself until the galaxies begin their final dance of destruction and rebirth that can last for billions of years. When galaxies collide, the stellar motions within each system become completely disrupted as gravitational forces reshape the orbital patterns that had persisted for billions of years, flinging some stars into intergalactic space, while compressing gas clouds to trigger massive bursts of star formation that can be observed across cosmic distances as some of the most luminous events in the universe. Our own Milky Way galaxy will experience such a merger in approximately 4.5 billion years, when the Andromeda galaxy, currently approaching us at 110 kilometers per second, finally arrives after its 2.5 million light-year journey to create what astronomers have dubbed Milkomeda, a new elliptical galaxy formed from the gravitational merger of two major spiral systems. Computer simulations of this future collision show that while individual stellar collisions will be extremely rare due to the vast distances between stars, the gravitational interactions will completely reshape both galaxies, ejecting some stars into intergalactic space while funneling others toward the combined galactic center, where the supermassive black holes from both galaxies will eventually merge in a cataclysmic release of gravitational energy. The space between galaxies and clusters is not empty, but filled with hot, tenuous gas at temperatures of millions of degrees, heated to such extreme conditions by the gravitational energy released during cluster formation, and maintained at these temperatures by ongoing motions within the cluster as galaxies orbit the cluster center and smaller groups fall inward under gravitational attraction. This intra-cluster medium contains more mass than all the visible stars in cluster galaxies combined, forming vast halos of superheated plasma that emit X-rays detectable by space-based telescopes and provide direct evidence for the enormous gravitational potential wells created by dark matter, concentrations that bind galaxy clusters together despite the high velocities of individual galaxies within them. The formation of large-scale structure throughout the universe results entirely from gravitational motion, amplifying tiny density fluctuations that originated as quantum fluctuations in the early universe, with regions slightly denser than average gradually attracting surrounding matter through gravitational collapse, while less dense regions became cosmic voids as matter flowed out of them toward the growing concentrations that would eventually become galaxy clusters and superclusters. This process of structure formation continues today as we observe galaxy clusters merging to form even larger systems, gas flowing along cosmic filaments toward growing concentrations of dark matter, and the overall cosmic web evolving through purely gravitational dynamics that demonstrate how motion shapes the universe on the largest possible scales. Modern surveys mapping the positions and velocities of millions of galaxies across billions of light years reveal that this cosmic motion follows predictable patterns determined by the distribution of dark matter, with galaxies flowing along filaments like rivers toward the nodes where clusters form, creating a dynamic tapestry of motion that connects the smallest scales of galactic rotation to the largest scales of cosmic evolution. The Hubble Space Telescope and other instruments have captured images of galaxy clusters in the process of merging, showing how these cosmic collisions create shock waves in the intracluster medium, trigger starbursts in member galaxies, and generate some of the most powerful sources of some X-ray and radio emission in the universe through the conversion of gravitational potential energy into thermal and magnetic energy during these spectacular cosmic crashes. Even the cosmic microwave background radiation carries the imprint of this large-scale motion through tiny temperature fluctuations caused by the Doppler effect as our local group moves through space, providing a cosmic reference frame against which all other motions can be measured, and demonstrating that motion permeates every aspect of cosmic evolution, from the quantum fluctuations that seed structure formation to the ongoing flows of matter and energy that continue shaping the universe billions of years after the Big Bang. In 1929, astronomer Edwin Hubble made one of the most profound discoveries in the history of science when he observed that distant galaxies are moving away from us with their recession velocities directly proportional to their distances from Earth, in a relationship that would become known as Hubble's law and fundamentally transform our understanding of the universe itself. Using the powerful Mount Wilson telescope, Hubble measured the redshift of light from distant galaxies, finding that their spectral lines were systematically shifted toward longer, redder wavelengths and wavelengths, in a way that could only be explained by the Doppler effect caused by these entire stellar systems racing away from our cosmic neighbourhood at tremendous speeds. The mathematical relationship Hubble discovered can be expressed simply as recession velocity equals the Hubble constant times distance, with the current best estimate for this constant being approximately 70 km per second per megaparsec, meaning that for every 3.26 million light years of distance, galaxies recede from us 70 km per second faster, creating a cosmic symphony of motion where the most distant observable galaxies retreat at significant fractions of the speed of light itself. This discovery revealed something far more extraordinary than merely distant galaxies racing through space away from our location, because the pattern Hubble observed indicated that space itself is expanding, carrying galaxies apart like raisins in a loaf of rising bread, where the dough between the raisins grows larger, while the raisins themselves remain unchanged. The expansion of space represents a fundamentally different kind of motion than anything humans had previously conceived, not objects moving through a static background, but the very fabric of reality continuously growing larger, stretching the distances between galaxy clusters while leaving the internal structure of gravitationally bound systems like galaxies and solar systems essentially unaffected by this cosmic growth. The cosmic microwave background radiation provides compelling evidence for this universal expansion, carrying the stretched and cooled remnant of the intense heat that filled the early universe when it was much smaller and denser than today, with this ancient light now detectable as faint radio waves that have been redshifted by a factor of more than 1,000 during their 13.8 billion year journey through expanding space. Perhaps the most remarkable aspect of cosmic expansion is that it has no centre, with every point in the universe appearing to be the centre of expansion from the perspective of observers at that location, creating a situation where galaxies in every direction appear to be receding according to the same Hubble relationship regardless of where you happen to be positioned in the cosmic web. This centraless expansion emerges naturally from the mathematics of general relativity applied to a homogeneous and isotropic universe where the curvature of space-time itself creates the expansion without requiring any special location or direction in space, making every galaxy an equally valid reference point for measuring cosmic motion. The expansion rate itself has changed throughout cosmic history, initially much faster during the brief period of cosmic inflation that occurred in the first fraction of a second after the Big Bang, then gradually slowing as matter and radiation dominated the universe's energy budget, and more recently accelerating again due to the mysterious influence of dark energy that now comprises roughly 68% of the total cosmic energy density. Modern precision measurements using Type Ia supernovae as standard candles have revealed that this acceleration began approximately 4 billion years ago, when dark energy's repulsive influence finally overcame the attractive force of gravity on cosmic scales, marking a transition from decelerated to accelerated expansion that will likely continue for the indefinite future unless some unknown physics intervenes. The implications of cosmic expansion extend far beyond academic cosmology, fundamentally altering our conception of time, space, and causality by demonstrating that the universe has a finite age and evolutionary history, that the cosmic horizon limits how far we can observe regardless of the power of our telescopes, and that the very notion of distance becomes ambiguous when applied to objects so far away that light from them began its journey billions of years ago when the universe was significantly smaller than it is today. Current observations suggest that space expands fast enough at the largest scales to carry the most distant observable galaxies away from us at velocities exceeding the speed of light. Not because these galaxies are moving through space faster than light, which would violate special relativity, but because the space between us and these distant objects grows at a rate that creates recession velocities greater than light speed when measured across cosmic distances. This cosmic motion affects even the most fundamental properties of electromagnetic radiation, stretching not only the wavelengths of light from distant sources, but also the duration of cosmic events as observed from Earth, creating a time dilation effect where distant supernovae appear to explode in slow motion due to the expansion of space during the time their light travels toward us. The expansion of space represents the ultimate form of motion in the universe, a movement so fundamental that it affects every photon of light, every measurement of distance, and every calculation of cosmic time, ensuring that the universe remains forever dynamic, and that perfect cosmic stillness is not only impossible on small scales due to quantum mechanics, but also impossible on large scales due to the inexorable expansion of space-time itself. In 1998, 2 independent teams of astronomers studying distant supernovae made a discovery that shocked the scientific world and earned them the Nobel Prize in Physics. The expansion of the universe is not slowing down as everyone expected, but instead accelerating at an ever-increasing rate driven by a mysterious force that physicists have dubbed dark energy. This discovery emerged from observations of Type Ia supernovae, stellar explosions that serve as cosmic standard candles because they always reach the same peak brightness, allowing astronomers to determine their distances by measuring how dim they appear from Earth, and then compare those distances to the recession velocities revealed by their redshifts. When the supernova data was analysed, it showed that distant supernovae were fainter than expected for their redshifts, indicating they were farther away than predicted by models of a decelerating universe, which could only be explained if cosmic expansion has been speeding up over the past several billion years, rather than gradually slowing down under the influence of gravitational attraction between matter and energy. Dark energy now appears to comprise approximately 68% of the total energy density of the universe, making it the dominant component of cosmic evolution, even though its fundamental nature remains one of the greatest mysteries in modern physics, with various theoretical proposals ranging from a cosmological constant representing the energy of empty space itself to exotic quantum fields with unusual properties that change over cosmic time. The cosmological constant, originally introduced by Einstein as a mathematical device to create a static universe before Hubble's discovery of expansion, has been resurrected as the simplest explanation for dark energy, representing a uniform energy density inherent in the vacuum of space that creates a repulsive gravitational effect opposing the attractive influence of ordinary matter and radiation. If dark energy behaves like a true cosmological constant with unchanging energy density even as space expands, then the acceleration of cosmic expansion will continue indefinitely into the future, ultimately leading to a scenario cosmologists call the Big Rip, where the expansion rate grows so extreme that it eventually overcomes all the fundamental forces holding matter together. In this distant future, perhaps 22 billion years from now, the expansion of space will become so violent that it first separates galaxy clusters, then tears apart individual galaxies, then disrupts solar systems and planetary orbits, and finally rips apart molecules, atoms, and even atomic nuclei in a cosmic crescendo of accelerating destruction that represents the ultimate triumph of expansion over all forms of gravitational and electromagnetic binding. Current observations indicate that space is already expanding faster than the speed of light at distances beyond our cosmic horizon, not because the expansion itself violates relativity, but because when you add up the expansion rate across billions of light years of distance, the cumulative recession velocity can exceed light speed, even though no local region of space expands faster than light, creating a cosmic horizon beyond which galaxies become forever unreachable no matter how long we wait or how fast we travel. This acceleration affects not only the most distant reaches of the observable universe, but also the future evolution of our own cosmic neighbourhood, as the accelerating expansion gradually increases the distances between galaxy clusters and will eventually carry even nearby groups of galaxies beyond our observational reach, leaving future civilizations in an ever more isolated and apparently static universe, where evidence for the Big Bang and cosmic evolution becomes increasingly difficult to detect. The energy required to drive this acceleration is enormous, roughly equivalent to adding 3 hydrogen atoms worth of mass energy to every cubic meter of space every billion years. Yet this energy appears from nowhere and requires no source or fuel, making dark energy a form of cosmic motion that seems to violate our everyday understanding of energy conservation, while somehow maintaining consistency with the fundamental laws of physics. Modern experiments using increasingly sophisticated techniques continue to refine measurements of dark energy's properties, searching for evidence that its density might be changing over time, or that its effects might vary with cosmic location, discoveries that could provide crucial clues about the underlying physics responsible for this mysterious acceleration that dominates the universe's current behaviour and future evolution. The study of dark energy represents one of the most active frontiers in contemporary physics and astronomy, with planned space missions and ground-based surveys designed to trace cosmic expansion history with unprecedented precision and potentially reveal whether dark energy is truly constant or represents some more complex phenomenon that will determine whether the universe ends in a Big Rip, eternal expansion, or some currently unimaginable cosmic transformation. Regardless of dark energy's ultimate nature, its discovery has demonstrated that motion dominates the universe even on the largest scales, ensuring that cosmic stillness remains impossible not only because of quantum fluctuations and thermal motion at small scales, but also because of the fundamental dynamics of space-time itself, which continues expanding and accelerating in ways that make the universe an eternally dynamic and evolving system, where change and motion are woven into the very fabric of reality. The universe's motion through time tells an extraordinary story of evolving dynamics that began 13.8 billion years ago with the Big Bang, when all of space, time, matter, and energy erupted from an initial singularity and immediately entered a period of exponential expansion called cosmic inflation that stretched space itself faster than the speed of light for a brief fraction of a second, growing the observable universe from subatomic scales to astronomical dimensions in less time than it takes light to cross a proton. This inflationary period represents the most extreme form of cosmic motion ever experienced, expanding space by factors of at least 10 to the 26th power and smoothing out any initial irregularities while simultaneously stretching quantum fluctuations to macroscopic scales where they would eventually serve as the seeds for all cosmic structure formation, including galaxies, stars, and planets billions of years in the future. Following inflation, the universe entered the radiation-dominated era, when photons, neutrinos, and other relativistic particles controlled cosmic dynamics through their enormous energy density, creating a hot, dense plasma where matter and radiation remained tightly coupled through constant interactions that prevented the formation of any stable structures larger than atomic nuclei. During this period lasting roughly 380,000 years, the universe expanded and cooled according to well-understood thermodynamic principles, with temperature dropping inversely proportional to the cosmic scale factor, and the energy density of radiation falling as the fourth power of the temperature, creating a cosmic environment where thermal motion dominated all other forms of motion and prevented the gravitational collapse that would later enable structure formation. The transition from radiation domination to matter domination marked a crucial turning point in cosmic evolution, when the universe finally became cool enough for electrons to combine with protons and form neutral hydrogen atoms, ending the cosmic dark age and allowing light to travel freely through space for the first time, while simultaneously enabling gravity to begin organizing matter into the first cosmic structures. Throughout the matter-dominated era, which lasted approximately 9 billion years, gravitational motion gradually amplified the tiny density fluctuations left over from inflation, causing regions slightly denser than average to attract surrounding matter and grow into increasingly massive concentrations, while less dense regions evolved into cosmic voids as matter flowed out of them toward the growing gravitational wells that would become galaxy clusters and superclusters. This process of hierarchical structure formation demonstrates how motion on small scales combines to create organization on large scales, with thermal motion of gas particles enabling gravitational collapse, orbital motion stabilizing the resulting structures, and continued accretion through gravitational motion building increasingly complex cosmic architecture over billions of years of cosmic evolution. Approximately 5 billion years ago, the universe entered its current dark energy-dominated era, when the mysterious repulsive force driving cosmic acceleration finally overcame the attractive influence of matter and radiation, fundamentally altering the future trajectory of cosmic evolution by ensuring that expansion will continue accelerating rather than eventually reversing into a big crunch scenario. This transition represents the most recent phase change in the universe's evolutionary history and determines that all future cosmic motion will be dominated by the accelerating expansion of space itself, gradually separating galaxy clusters beyond the reach of light-speed communication, and ultimately leading to an increasingly cold, dark, and isolated cosmos where individual galaxy groups become island universes surrounded by ever-growing volumes of empty space. Current cosmological models predict several possible scenarios for the far future of cosmic motion, ranging from eternal exponential expansion driven by constant dark energy density to more exotic possibilities such as the Big Rip, where accelerating expansion eventually overcomes all fundamental forces and tears apart every structure in the universe, or phantom dark energy scenarios where the acceleration itself accelerates until space-time itself becomes unstable and cosmic evolution enters completely unknown territory. Even in the most conservative projections where dark energy remains constant and expansion continues at an accelerating but stable rate, the universe will eventually reach a state where all stars have burned out, all black holes have evaporated through Hawking radiation, and only elementary particles remain in a cold, expanded cosmos where quantum fluctuations represent the only remaining form of motion across vast volumes of space containing virtually no matter or energy. Yet even in this ultimate heat-death scenario, motion never completely ceases because quantum mechanics ensures that zero-point fluctuations persist even at absolute zero temperature. Virtual particles continue appearing and disappearing in the vacuum, and the fundamental uncertainty principle maintains its prohibition against perfect stillness at any scale, demonstrating that motion remains an inescapable feature of reality from the quantum foam to cosmic expansion throughout all of cosmic history, from the Big Bang to the far future when the universe may expand into a state of maximum entropy, but never perfect stillness. Light travels through the universe at exactly 299 to 792,458 meters per second, a velocity so fundamental to the structure of reality that it defines the maximum possible speed for any form of matter, energy, or information transfer, making electromagnetic radiation the ultimate form of cosmic motion that connects every corner of the observable universe through an intricate network of oscillating electric and magnetic fields. Electromagnetic waves represent a unique form of motion where no physical substance actually travels from source to destination, but rather disturbances in electric and magnetic fields propagate through space by continuously regenerating each other in a self-sustaining dance where changing electric fields create magnetic fields, and changing magnetic fields create electric fields in an endless cycle that requires no medium and can traverse the complete vacuum of interstellar and intergalactic space. These waves carry both energy and momentum despite having no mass, demonstrating that motion and momentum are more fundamental than matter itself, with photons serving as discrete packets of electromagnetic energy that can transfer their motion to matter through processes ranging from the gentle warming of your skin by sunlight to the violent acceleration of particles in cosmic ray showers generated by the most energetic gamma rays in the universe. The electromagnetic spectrum encompasses an enormous range of frequencies and wavelengths, from radio waves with wavelengths longer than buildings to gamma rays with wavelengths smaller than atomic nuclei, yet every form of electromagnetic radiation travels at precisely the same speed through vacuum regardless of its energy, frequency or wavelength, creating a cosmic democracy of motion where the faintest radio whisper from a distant pulsar and the most intense gamma ray burst from an exploding star both participate equally in the universal speed limit that governs all electromagnetic phenomena. Doppler shifts in electromagnetic radiation provide astronomers with the most powerful tool for detecting and measuring motion throughout the universe. As the motion of any source toward or away from an observer creates characteristic changes in the observed frequency and wavelength of its emitted light, radio waves or other electromagnetic signals that reveal not only the velocities of stars, galaxies, and gas clouds, but also enable precise measurements of cosmic expansion, stellar rotation rates, and the orbital motion of planets around distant stars. When a source moves toward an observer, its electromagnetic radiation becomes compressed to higher frequencies and shorter wavelengths in a phenomenon called blue shift, while sources moving away from the observer show redshift, where radiation is stretched to lower frequencies and longer wavelengths, effects that become more pronounced at higher velocities and enable astronomers to measure recession speeds approaching significant fractions of light speed for the most distant observable galaxies. Electromagnetic radiation serves as the primary mechanism for energy transfer throughout the universe, carrying the nuclear energy generated in stellar cores across vast distances to power planetary atmospheres, drive chemical reactions, and enable the complex photochemistry that makes life possible on worlds orbiting stars throughout the galaxy, while also redistributing thermal energy between cosmic structures and maintaining the temperature balance that determines the physical state of matter in different cosmic environments. The interaction between electromagnetic radiation and matter creates countless forms of motion as photons are absorbed, scattered, and re-emitted by atoms and molecules, transferring momentum and energy that can heat gases to millions of degrees in stellar coronae, accelerate charged particles to relativistic speeds in magnetic field regions around neutron stars and black holes, and drive the complex atmospheric dynamics that create weather patterns on planets throughout the solar system. Solar radiation pressure, though incredibly weak by everyday standards, represents a significant force in the space environment where it can alter the orbits of small particles, power solar sails for spacecraft propulsion, and create the beautiful comet tails that stream away from the sun as solar photons push dust and gas particles outward through pure momentum transfer from electromagnetic radiation to matter. The speed of light also sets fundamental limits on causality and communication throughout the universe, ensuring that no information or influence can travel faster than electromagnetic signals, and creating light speed delay effects that mean we always observe distant objects as they existed in the past, rather than as they appear in the present moment, making astronomy inherently a study of cosmic history, where looking deeper into space automatically means looking further back in time. Modern technology exploits electromagnetic motion in countless ways, from the radio waves that enable global communication and satellite navigation, to the infrared radiation used in thermal imaging, and the X-rays employed in medical diagnostics and astronomical observations, demonstrating how understanding electromagnetic motion has become essential for virtually every aspect of modern civilization, while also providing the tools needed to explore the universe across the entire electromagnetic spectrum. Even quantum mechanics reveals that electromagnetic radiation exhibits both wave and particle properties depending on how it is observed, with individual photons behaving as discrete particles when detected, yet displaying wave-like interference and diffraction patterns when traveling through space, suggesting that the fundamental nature of electromagnetic motion transcends simple classical concepts and connects to the deeper quantum mechanical principles that govern all forms of motion and energy throughout the universe. Moving electric charges create magnetic fields around them in one of the most fundamental relationships in physics, discovered through centuries of careful experimentation that revealed the deep connection between electricity and magnetism as manifestations of a single electromagnetic force that governs countless phenomena, from the operation of electric motors to the generation of cosmic magnetic fields around rotating neutron stars. When electric current flows through a wire, it generates circular magnetic field lines that wrap around the conductor, with the strength and direction of these fields determined by the amount of current and following precise mathematical relationships that enable engineers to design everything from simple electromagnets to the superconducting magnets used in particle accelerators and magnetic resonance imaging machines. The reverse relationship, where changing magnetic fields create electric fields, completes the electromagnetic circle and enables the process of electromagnetic induction that forms the basis for electric generators, transformers, and countless other technologies that convert mechanical motion into electrical energy or transfer electrical power between different voltage levels through the controlled manipulation of magnetic flux. This electromagnetic induction occurs whenever magnetic field lines move relative to electrical conductors, inducing currents that flow in directions determined by Lenz's law to oppose the change in magnetic flux that created them, ensuring conservation of energy while enabling the conversion of kinetic energy from falling water, steam turbines, or wind into the electrical energy that powers modern civilization. The solar wind provides one of the most spectacular examples of electromagnetic motion on cosmic scales, as our Sun continuously streams charged particles into space at velocities averaging 400 kilometers per second, carrying with them frozen-in magnetic field lines that create the interplanetary magnetic field extending throughout the solar system and beyond into interstellar space, where it helps shape the boundary between our local stellar environment and the broader galactic medium. These solar wind particles, primarily protons and electrons accelerated by the extreme temperatures and magnetic fields in the solar corona, travel outward from the Sun at supersonic speeds, while following complex trajectories influenced by their own magnetic fields and the rotating magnetic field structure of the Sun, creating a dynamic system where electromagnetic forces continuously accelerate charged particles and transfer energy across astronomical distances. Earth's magnetic field lines exist in constant flux as they respond to the varying pressure and magnetic field orientation of the solar wind, creating a complex interaction region called the magnetosphere, where terrestrial and interplanetary magnetic fields merge, reconnect, and reconfigure in processes that store and release enormous amounts of electromagnetic energy through phenomena such as magnetic substorms and geomagnetic storms. The motion of charged particles within these magnetic field configurations creates some of the most beautiful displays in nature, when high-energy electrons and protons spiral down magnetic field lines into Earth's upper atmosphere, colliding with oxygen and nitrogen molecules to create the aurora borealis and aurora australis that paint the polar skies with curtains of green, red, and blue light moving and shifting in response to the constant flux of electromagnetic forces. These auroral displays serve as visible evidence that electromagnetic fields throughout the universe are never truly static but exist in states of perpetual motion and change, with field lines stretching, compressing, breaking, and reconnecting as they respond to the motion of charged particles and the changing conditions in the plasma environments where electromagnetic forces dominate over gravitational and other influences. Magnetic field lines themselves represent a useful conceptual tool for visualizing electromagnetic motion, but it's important to understand that these lines are not physical entities, but rather mathematical representations of field strength and direction that help us comprehend how electromagnetic forces guide the motion of charged particles along curved paths through three-dimensional space. The constant motion of charged particles in cosmic magnetic fields creates phenomena ranging from the radio waves emitted by electrons spiraling around magnetic field lines in supernova remnants to the intense X-ray radiation generated when matter falls into black holes and becomes heated to millions of degrees while following magnetic field lines in accretion disk structures. Electromagnetic induction also operates on cosmic scales when conducting materials such as ionized gas move through magnetic fields, inducing electric currents that can power stellar magnetic fields through dynamo processes where the rotation and convection of electrically conducting fluids in stellar interiors generate and maintain magnetic fields that persist for billions of years while continuously evolving in response to changing internal conditions. Modern spacecraft and satellites must be designed to withstand the electromagnetic environment of space, where solar wind particles, cosmic rays and varying magnetic fields can induce electrical currents in metal structures, disrupt electronic systems, and create charging effects that pose significant engineering challenges for missions operating in the harsh electromagnetic environment beyond Earth's protective atmosphere. The study of electromagnetic motion has revealed that magnetic and electric fields store energy that can be suddenly released through reconnection events, where oppositely directed magnetic field lines come together and annihilate each other while converting magnetic field energy into kinetic energy of accelerated particles, heating, and electromagnetic radiation in processes that power solar flares, drive auroral substorms, and may contribute to heating the solar corona to temperatures exceeding 1 million degrees Celsius. 99% of the visible universe exists in the plasma state, where electrons have been stripped from atomic nuclei by extreme temperatures or intense radiation, creating an ionized gas that behaves according to the complex laws of magnetohydrodynamics and participates in some of the most energetic and spectacular forms of motion observed anywhere in the cosmos. Unlike the familiar matter we encounter in everyday life, plasma responds to both gravitational and electromagnetic forces, allowing magnetic fields to guide and accelerate charged particles to incredible velocities, while also enabling the storage and sudden release of enormous amounts of energy through magnetic reconnection events that can heat plasma to temperatures of millions or even billions of degrees. Solar plasma demonstrates these principles on a scale we can observe in detail, as the Sun's outer atmosphere consists entirely of ionized hydrogen and helium at temperatures exceeding 1 million degrees Celsius, hot enough to strip electrons from atoms and create a dynamic environment where magnetic field lines constantly emerge, evolve, and reconnect, while carrying plasma along complex three-dimensional trajectories that can suddenly erupt in solar flares, releasing the energy equivalent of billions of hydrogen bombs. These solar flares occur when magnetic field lines become twisted and stressed by this differential rotation of the Sun's surface, storing magnetic energy that eventually reaches a critical point where the field lines snap and reconnect, instantly converting magnetic field energy into kinetic energy that accelerates plasma particles to significant fractions of light speed and hurls them across the solar system in coronal mass ejections that can disrupt satellite communications and power grids when they interact with Earth's magnetosphere. Magnetohydrodynamics governs the behavior of cosmic plasma by combining the equations of fluid dynamics with Maxwell's equations of electromagnetism, creating a theoretical framework that explains how plasma can be confined by magnetic fields, accelerated along field lines, and heated through various instabilities and wave phenomena that convert magnetic and kinetic energy into thermal energy through complex nonlinear processes. Stellar winds represent another fundamental form of plasma motion, as stars throughout the galaxy continuously emit streams of charged particles that escape the gravitational pull of their parent stars and flow outward into interstellar space at velocities ranging from hundreds to thousands of kilometers per second, carrying magnetic field lines with them, and creating vast cavities in the interstellar medium called stellar wind bubbles, where the pressure of the outflowing plasma exceeds the pressure of the surrounding gas and dust. When stellar winds encounter planetary magnetospheres, they create complex interaction regions where the planet's magnetic field deflects and channels the incoming charged particles, sometimes funneling them toward the magnetic poles where they create aurora displays, but also providing protection from harmful radiation by preventing most stellar wind particles from reaching planetary surfaces and stripping away atmospheric gases. Cosmic rays represent the most extreme form of plasma motion in the universe, consisting of atomic nuclei and electrons that have been accelerated to energies billions of times higher than anything achievable in terrestrial particle accelerators, traveling through interstellar and intergalactic space at velocities so close to light speed that relativistic effects become significant, and these particles can traverse the entire galaxy in relatively short periods of cosmic time. The acceleration mechanisms that create cosmic rays remain partially mysterious, but they likely involve shock waves from supernova explosions, magnetic reconnection events around neutron stars and black holes, and other high-energy astrophysical processes where electromagnetic fields can tap into gravitational or rotational energy sources and convert them into the kinetic energy of individual particles moving at relativistic speeds. Perhaps the most spectacular examples of plasma motion occur in the relativistic jets emitted by supermassive black holes at the centers of active galaxies, where matter falling into the black hole becomes heated to billions of degrees, and channeled along magnetic field lines into narrow beams that extend for thousands of light years across intergalactic space, while maintaining their coherence and travelling at speeds exceeding 99% of light velocity. These jets demonstrate the power of the magnetohydrodynamic processes to organise plasma motion on truly cosmic scales, extracting rotational energy from spinning black holes through magnetic field interactions, and converting it into directed kinetic energy that can transport matter and energy across distances comparable to the size of galaxy clusters, while creating some of the most luminous and energetic phenomena observable in the universe. The study of plasma physics has revealed that this fourth state of matter exhibits collective behaviours that emerge from the coordinated motion of billions of charged particles responding to electromagnetic fields, creating phenomena such as plasma waves, magnetic reconnection, and turbulence that redistribute energy and momentum in ways that can dramatically alter the evolution of astrophysical systems from planetary magnetospheres to the intergalactic medium itself. Every particle in the universe, from the electrons flowing through your nervous system to the photons carrying sunlight across 93 million miles of space, represents nothing more than a localized excitation or vibration in underlying quantum fields that permeate every point in the cosmos, filling all of space with invisible energy and information that forms the deepest foundation of physical reality. These quantum fields exist everywhere simultaneously, with electron fields, photon fields, quark fields, neutrino fields, and fields for every known particle type occupying the same regions of space while maintaining their distinct identities through different mathematical properties and interaction rules that determine how they respond to each other and manifest as the particles we observe in experiments and cosmic phenomena. The electron field that fills the universe carries the potential for electrons to appear anywhere at any time when sufficient energy becomes available to create particle-antiparticle pairs from the vacuum, while the photon field enables electromagnetic radiation to propagate through apparently empty space by providing the medium through which electric and magnetic field oscillations can travel at light speed across cosmic distances. Field fluctuations driven by the uncertainty principle ensure that these quantum fields never remain perfectly static, but instead undergo constant random variations in energy and field strength that occasionally become large enough to manifest as virtual particles, fleeting excitations that borrow energy from the vacuum for time so brief that they cannot be directly detected, yet play crucial roles in mediating forces and determining the properties of matter throughout the universe. Quantum field theory represents our most successful description of physical reality, providing a mathematical framework that unifies special relativity with quantum mechanics while explaining how particles can be created and destroyed, how forces operate through field interactions, and why certain fundamental symmetries and conservation laws govern all physical processes from radioactive decay to the formation of galaxies. These fields know about each other through constant interaction, mediated by virtual particle exchanges, creating an interconnected network where every field continuously influences every other field through quantum, mechanical processes that operate faster than any classical signal could travel, establishing correlations and maintaining consistency across cosmic distances through purely quantum mechanical means. The concept of truly empty space becomes meaningless in quantum field theory because removing all particles from a region still leaves behind the quantum fields themselves, which cannot be eliminated any more than you could remove the concept of temperature or pressure from a volume of gas, making the quantum vacuum a dynamic medium filled with field fluctuations rather than the static nothingness that classical physics might suggest. Every point in space contains infinite numbers of quantum oscillators corresponding to all possible field modes and particle types, each oscillator contributing its zero-point energy to the vacuum, while also providing pathways for virtual particle creation and annihilation that ensure constant activity, even in the apparent emptiness between galaxies where matter density drops to less than 1 proton per cubic meter. The standard model of particle physics describes how 12 fundamental matter fields and 4 force fields interact to create all known phenomena, with each field having characteristic properties such as mass, electric charge, and coupling strengths that determine how strongly they interact with other fields and what types of particles can emerge from their excitations. Particle creation occurs when energy input to a quantum field exceeds the threshold required to create real excitations that can persist and propagate through space, whether through high-energy collisions in particle accelerators, nuclear reactions in stellar cores, or cosmic ray interactions in Earth's atmosphere where field excitations manifest as showers of secondary particles. Field interactions operate through the exchange of virtual particles that emerge from quantum fluctuations, travel between real particles, and return to the vacuum after transferring momentum, energy, or other quantum numbers, creating what we perceive as forces while actually representing the dynamical evolution of coupled quantum field systems responding to each other according to the equations of quantum field theory. Modern experiments can now manipulate quantum fields with extraordinary precision, creating situations where field properties become directly observable through phenomena such as the Casimir effect, laser-induced particle creation, and quantum entanglement experiments that demonstrate how field correlations can span arbitrary distances while maintaining instantaneous connections that transcend classical limitations on information transfer. The quantum fields that fill space also provide the stage for cosmic evolution, with field fluctuations during cosmic inflation becoming stretched to macroscopic scales, where they seeded the density variations that eventually grew into galaxies, stars, and planets through gravitational collapse, guided by the same field dynamics that govern particle interactions in laboratory experiments. Understanding quantum fields as the fundamental constituents of reality reveals that motion is built into the deepest level of existence, with field fluctuations ensuring that perfect stillness violates the basic principles of quantum mechanics, while field interactions create the forces and particle exchanges that drive all physical processes from chemical reactions to stellar nucleosynthesis to the expansion of space itself. Einstein's revolutionary equation E=mc² reveals that mass and energy are fundamentally interchangeable, allowing pure kinetic energy to transform into matter, and enabling the creation of particles from nothing more than concentrated motion and electromagnetic radiation in processes that demonstrate the deep unity between matter, energy, and the geometry of space-time itself. Particle accelerators exploit this mass-energy equivalence by accelerating protons, electrons, or other particles to velocities approaching the speed of light, then smashing them together with such tremendous kinetic energy that the collision creates entirely new particles that did not exist before the impact, converting the organized motion of the accelerated beams into the rest mass of exotic particles such as muons, pions, strange quarks, and even the Higgs boson that was discovered at the Large Hadron Collider through precisely such high-energy collisions. These accelerator experiments demonstrate that motion itself can become matter when sufficient energy concentrates in a small enough region of space, with the newly created particles emerging from the collision point and travelling outward through sophisticated detector systems that measure their properties, lifetimes, and decay products to verify theoretical predictions about the fundamental structure of matter and the forces that govern particle interactions. Cosmic ray collisions provide nature's own particle accelerators on a scale that dwarfs anything humans have built, as high-energy protons and atomic nuclei from distant astrophysical sources crash into Earth's atmosphere with energies millions of times greater than terrestrial accelerators can achieve, creating cascading showers of secondary particles that rain down continuously across the planet's surface, while demonstrating that particle creation from pure kinetic energy occurs naturally throughout the universe, wherever sufficient concentrations of motion and energy come together. When a cosmic ray proton travelling at 99.9% of light speed strikes an atmospheric nucleus, the collision instantly creates dozens of new particles, including pions, kaons, and other unstable particles that decay within microseconds into muons, electrons, photons, and neutrinos that continue downward through the atmosphere, with some muons possessing enough energy to penetrate deep underground, where they can be detected in specially designed experiments that use cosmic ray interactions to study both particle physics and the astronomical sources of these ultra-high energy particles. Hawking radiation represents perhaps the most exotic form of particle creation, occurring near black holes where the extreme curvature of spacetime creates conditions so intense that virtual particle pairs from quantum field fluctuations can become separated before annihilating each other, allowing one member of the pair to escape as real radiation while the other falls into the black hole, slowly reducing the black hole's mass through this quantum mechanical process that converts gravitational energy into thermal radiation, with a temperature inversely proportional to the black hole's mass. This process demonstrates that even the most extreme gravitational fields in the universe cannot prevent quantum motion and particle creation. With the event horizon of a black hole acting like a one-way membrane, that allows virtual particles to become real through the energy provided by the black hole's gravitational field, ensuring that even these cosmic monsters will eventually evaporate completely through the steady emission of Hawking radiation over timescales that exceed the current age of the universe by about many orders of magnitude. Spontaneous pair production occurs when electromagnetic fields become strong enough to extract electron-positron pairs directly from the quantum vacuum, a process that requires field strengths approaching 10 to the 16 volts per meter but can occur naturally near the surfaces of neutron stars, in the intense electromagnetic environments around black holes, or in laboratory experiments using the most powerful laser systems where focused light beams create field intensities sufficient to trigger vacuum breakdown and materialize matter from apparently empty space. Conservation laws govern all particle creation and annihilation processes, ensuring that fundamental quantities such as electric charge, energy, momentum, and various quantum numbers remain balanced in every transformation, with particles always created in pairs that cancel each other's conserved properties, or emerging from interactions where the total amount of each conserved quantity remains constant before and after the event. The study of particle creation and annihilation has revealed that the universe operates like a vast recycling system, where matter and energy continuously transform between different forms while respecting absolute conservation principles, with every particle creation event balanced by corresponding annihilation processes, and every transformation governed by the same fundamental symmetries that determine the structure of physical laws throughout the cosmos. Modern experiments can now observe individual particle creation and annihilation events in real time, using sophisticated detector technologies that reveal how quantum field fluctuations, electromagnetic radiation, and kinetic energy can all contribute to the ongoing dance of creation and destruction that characterizes the quantum vacuum and ensures that motion and change occur even at the most fundamental levels of physical reality, where particles emerge from and return to the underlying field structures that form the true foundation of everything we observe in the universe. All fundamental forces in the universe operate through the continuous exchange of virtual particles between matter, revealing that what we perceive as pushes and pulls are actually manifestations of quantum field interactions where force-carrying particles emerge from vacuum fluctuations, travel between objects, and disappear back into the quantum foam after transferring momentum, energy, and other properties that create the attractive and repulsive effects we observe as gravitational, electromagnetic, and nuclear forces. The electromagnetic force, which governs everything from chemical bonding to the operation of electric motors, operates through the constant exchange of virtual photons that flicker back and forth between electrically charged particles, with each photon carrying a tiny amount of momentum that accumulates over countless exchanges to create the macroscopic forces we measure in laboratory experiments and observe in natural phenomena ranging from lightning bolts to the aurora displays that illuminate polar skies. Virtual photons differ from real photons in that they cannot be directly detected or observed, existing only during the brief moments when they travel between charged particles before being absorbed and their energy returned to the quantum vacuum. Yet these invisible messengers carry enough momentum to hold atoms together, power stellar fusion reactions, and enable the electromagnetic radiation that carries information across cosmic distances at the speed of light. The weak nuclear force operates through much more massive virtual particles called W and Z bosons, discovered in particle accelerator experiments that confirmed theoretical predictions about these fundamental force carriers that mediate radioactive decay, enable nuclear fusion reactions in stellar cores, and govern the transformation of neutrons into protons and electrons that drives the nuclear processes powering stars throughout the universe. Because W and Z bosons possess significant rest mass unlike massless photons, the uncertainty principle limits how far they can travel before their borrowed energy must be repaid to the quantum vacuum, restricting the weak nuclear force to extremely short ranges measured in fractions of atomic nucleus diameters, and explaining why weak interactions occur much more slowly than electromagnetic processes, despite both forces having comparable intrinsic strengths. The strong nuclear force binds protons and neutrons together in atomic nuclei through the exchange of virtual gluons, massless particles that carry the color charge responsible for the strong interaction and exhibit the unique property of becoming stronger rather than weaker as quarks are pulled apart, creating a force that increases with distance until it becomes energetically favorable to create new quark-antiquark pairs rather than separate existing quarks beyond a certain distance threshold. This unusual behaviour of the strong force mediated by gluon exchanges that can themselves carry colour charge and interact with other gluons leads to the phenomenon of colour confinement, where individual quarks cannot exist in isolation but must always be bound together in groups that form colour-neutral particles such as protons, neutrons and other hadrons observed in high-energy physics experiments. Gravity remains the most mysterious of the fundamental forces because its hypothetical mediator, the graviton, has never been directly detected despite extensive theoretical work, suggesting that gravitational attraction should result from the exchange of massless, spin, two virtual particles that couple to the energy-momentum content of matter and spacetime rather than to electric charge or colour charge like the other force carriers. The extreme weakness of gravity compared to other fundamental forces makes graviton detection extraordinarily challenging, requiring sensitivity levels far beyond current experimental capabilities. Yet indirect evidence for gravitational waves detected by LIGO and other interferometers supports the theoretical picture of gravity as a field phenomenon that propagates at light speed through space-time disturbances created by accelerating masses. The range of each fundamental force depends critically on the mass of its mediating virtual particle, with massless mediators like photons and gluons creating infinite range forces, while massive mediators like W and Z bosons create short-range forces whose strength falls off exponentially with distance, demonstrating how the uncertainty principle governs not only the temporary existence of virtual particles, but also the macroscopic structure of forces that determine everything from atomic stability to the large-scale organization of matter throughout the universe. Virtual particle exchanges occur constantly throughout space and time, with every charged particle continuously emitting and absorbing virtual photons, every coloured particle exchanging virtual gluons, and every massive particle participating in weak interactions through virtual W and Z boson exchanges, creating a dynamic picture of reality where forces emerge from the coordinated motion of quantum fields rather than mysterious action at a distance effects that classical physics could never adequately explain. The uncertainty principle enables these virtual particle exchanges by allowing temporary violations of energy conservation, provided that the borrowed energy is repaid within time intervals determined by Heisenberg's uncertainty relation, making force interactions possible through quantum mechanical processes that would be forbidden in classical physics, and ensuring that the universe remains connected through constantly fluctuating field interactions that transfer information and momentum across all scales from subatomic particles to cosmic structures. Emmy Noether's profound theorem, formulated in 1915, establishes one of the most fundamental principles governing the universe by proving that every continuous symmetry in the laws of physics automatically generates a corresponding conservation law, creating an unbreakable mathematical connection between the geometric properties of space-time and the physical quantities that remain constant throughout all interactions and transformations. This theorem reveals that conservation of energy emerges directly from the symmetry of physical laws under time translation, meaning that because the fundamental equations of physics remain unchanged, whether an experiment is performed today or tomorrow, energy must be conserved in all processes, making the flow and transformation of energy between different forms an inevitable consequence of the universe's temporal symmetry. Conservation of energy requires continuous motion, because any system at perfect rest would violate energy conservation by failing to account for the kinetic energy associated with quantum zero-point motion, thermal vibrations, electromagnetic field fluctuations, and the countless other forms of energy that must remain active to maintain the dynamic equilibrium needed for energy conservation across all scales, from subatomic particles to cosmic structures. Conservation of momentum arises from the spatial symmetry of physical laws, specifically the fact that the laws of physics remain identical regardless of where in space an experiment is conducted, ensuring that in the absence of external forces, objects must continue moving with constant velocity rather than spontaneously coming to rest, because stopping would require the creation or destruction of momentum in violation of this fundamental conservation principle derived from spatial homogeneity. The conservation of angular momentum stems from rotational symmetry, the invariance of physical laws under rotation in space, which mandates that spinning objects continue rotating indefinitely unless acted upon by external torques, explaining why planets maintain their orbital motion around stars, why galaxies continue rotating for billions of years, and why even subatomic particles possess intrinsic angular momentum called spin that cannot be eliminated or reduced to zero. These conservation laws combine to make perfect stillness fundamentally impossible, because any hypothetical state of absolute rest would simultaneously violate multiple conservation principles, requiring the complete absence of kinetic energy, momentum, and angular momentum, while somehow maintaining the energy content needed to sustain the quantum fields, electromagnetic radiation, and thermal fluctuations that permeate all of space according to the laws of thermodynamics and quantum mechanics. Information flows constantly through quantum interactions as particles exchange momentum, energy, spin, and other conserved quantities in processes that transfer data about position, velocity, and internal states across space and time, creating an unbroken network of cause and effect relationships that connect every event in the universe to every other event, through chains of quantum mechanical interactions governed by conservation laws. The universe operates as a vast information processing system where every particle collision, field interaction, and quantum measurement contributes to the ongoing computation of physical reality, with conservation laws serving as the fundamental algorithms that determine how information can be created, transferred, and transformed while maintaining consistency across all scales from the Planck length to the cosmic horizon. Quantum entanglement demonstrates how conservation laws create instantaneous correlations between distant particles that share conserved properties, ensuring that measurements performed on one particle immediately determine the possible outcomes of measurements on its entangled partner, regardless of the spatial separation between them, showing that information about conserved quantities propagates through quantum mechanical channels that transcend classical limitations on communication speed. The symmetries underlying conservation laws also determine the structure of fundamental forces, with gauge symmetries generating the electromagnetic, weak and strong nuclear forces through mathematical transformations that leave the laws of physics unchanged, while creating the force-carrying particles and interaction rules that govern all matter and energy throughout the universe. Modern particle physics experiments continuously verify that conservation laws hold even in the most extreme conditions, from high-energy collisions in particle accelerators to the intense gravitational and electromagnetic fields around black holes and neutron stars, confirming that these principles represent absolute constraints on physical reality that cannot be violated by any known process or phenomenon. The combination of conservation laws with quantum uncertainty creates a universe where perfect predictability becomes impossible even as certain quantities remain absolutely conserved, leading to a cosmic reality where deterministic conservation principles coexist with fundamental randomness to produce the rich complexity and endless variety we observe in natural phenomena, from quantum fluctuations to biological evolution to stellar nuclear synthesis. These mathematical relationships between symmetry and conservation reveal that motion is not merely a property of matter, but rather a fundamental requirement built into the logical structure of physical reality, making stillness not just practically impossible but logically contradictory within any consistent description of a universe governed by the symmetries and conservation laws that define the mathematical framework of modern physics. The second law of thermodynamics stands as one of the most profound and inescapable principles governing the universe, stating that entropy must always increase in isolated systems, creating an irreversible arrow of time that drives motion throughout the cosmos as energy flows inexorably from concentrated, organized forms to dispersed, disordered distributions that can never spontaneously return to their original configurations. This fundamental law ensures that heat always flows from hot objects to cold objects, never the reverse, creating temperature gradients that drive convection currents in planetary atmospheres, power stellar evolution through nuclear fusion reactions, and enable the complex thermodynamic cycles that extract useful work from thermal energy differences in everything from steam engines to living organisms that depend on metabolic processes for survival, even at the theoretical maximum entropy state known as heat death. When the universe has reached perfect thermal equilibrium with matter and energy distributed as uniformly as possible throughout space, motion would still persist in the form of thermal vibrations, quantum fluctuations, and zero-point energy that cannot be eliminated even when all macroscopic temperature differences have disappeared and no useful work can be extracted from the system. Statistical mechanics reveals how the microscopic chaos of countless randomly moving particles gives rise to the macroscopic order we observe in thermodynamic processes, with the second law emerging not from the fundamental equations of motion themselves, which are reversible and could in principle run backward through time, but from the overwhelming statistical probability that systems will evolve toward configurations with higher entropy simply because there are vastly more disordered arrangements than ordered ones. The irreversibility that characterizes everyday experience emerges from reversible microscopic laws through the mathematics of large numbers, where individual molecular collisions follow perfectly timed symmetric rules, yet collectively produce irreversible behavior because the probability of spontaneous organization becomes vanishingly small when enormous numbers of particles interact randomly according to the laws of chance and statistical distribution. Molecular chaos ensures that even though every individual collision between atoms or molecules conserves energy and momentum while following deterministic physical laws, the combined effect of countless such interactions drives systems toward equilibrium through processes that appear irreversible on macroscopic scales, despite being built from fundamentally reversible microscopic components. The heat death scenario represents the ultimate fate of an expanding universe where entropy reaches its maximum possible value, leaving matter distributed uniformly at the lowest possible temperature, while space continues expanding and cooling, yet even this final state would contain minimum motion rather than zero motion, because quantum mechanics forbids absolute stillness and ensures that particles retain zero-point kinetic energy even in the absence of any thermal energy gradients. This cosmic end state would feature individual particles moving with random thermal velocities determined by the tiny residual temperature resulting from the expansion and cooling of space itself, while quantum field fluctuations continue creating virtual particles that appear and disappear according to the uncertainty principle, maintaining a baseline level of activity that represents the irreducible minimum motion compatible with the laws of quantum mechanics and thermodynamics. The approach to maximum entropy drives virtually every process we observe in the universe, from the nuclear fusion reactions that power stars by converting hydrogen into helium while radiating energy into space, to the chemical reactions that enable biological metabolism by breaking down organized molecules and dispersing their energy as heat, to the gravitational collapse of gas clouds that forms new stellar systems while converting gravitational potential energy into thermal and kinetic energy. Even the expansion of the universe itself represents a form of entropy. Increase as matter and energy spread across ever larger volumes of space, diluting the energy density and reducing the temperature of cosmic background radiation while creating the conditions for structure formation through gravitational instabilities that concentrate matter into galaxies, stars, and planets where local decreases in entropy occur at the expense of greater increases in the surrounding environment. The second law of thermodynamics thus creates a cosmic imperative for continuous motion and change, making it impossible for any system to achieve perfect equilibrium or absolute stillness, because the statistical mechanics underlying entropy increase requires ongoing molecular motion, particle interactions, and energy transfers that maintain the dynamic processes necessary for entropy production and the emergence of the timer-symmetric behavior that distinguishes past from future throughout the observable universe. Modern research into non-equilibrium thermodynamics has revealed how living systems and other complex structures can temporarily decrease their internal entropy by increasing the entropy of their surroundings, creating islands of organization and complexity that persist through constant energy consumption and waste heat production, demonstrating that even the most highly organized systems must participate in the universal trend toward entropy increase while using motion and energy flow to maintain their structure against the relentless tendency toward thermodynamic equilibrium that characterizes all isolated systems evolving according to the second law of thermodynamics. Motion stands as the fundamental property of existence itself, the irreducible essence that transforms mere potentiality into actual reality and makes the universe a dynamic, evolving system rather than a static collection of objects frozen in perfect stillness that would violate every principle of quantum mechanics, thermodynamics, and relativity, while failing to account for the continuous flow of energy and information that characterizes every level of physical reality from the quantum foam to cosmic expansion. At the smallest scales, quantum field fluctuations ensure that space itself seethes with virtual particle creation and annihilation events that occur trillions of times per second in every cubic centimetre of apparently empty vacuum, while at the largest scales the expansion of spacetime carries galaxy clusters apart at velocities that exceed the speed of light across cosmic horizons, demonstrating that motion permeates reality from the Planck length to the observable universe, without any scale of organisation where perfect stillness becomes possible or even meaningful. Consciousness itself emerges as a complex pattern of motion within neural networks where billions of neurons fire in coordinated sequences that process information through electrochemical signals travelling along axons and across synapses, creating the subjective experience of awareness through precisely orchestrated flows of ions, neurotransmitters, and electrical potentials that transform sensory input into memory, thought, and decision-making through processes that depend entirely on molecular motion and energy flow within living brain tissue. Information processing requires continuous energy flow because computation, whether performed by biological neural networks or electronic computers, involves the transformation of energy from one form to another as information moves through processing systems, with every logical operation, memory storage event, and data transmission consuming energy while generating heat according to the fundamental thermodynamic limits established by information theory and statistical mechanics. Life represents the most sophisticated form of organised motion yet discovered in the universe, with living organisms extracting energy from their environment through metabolism and using that energy to maintain complex molecular structures, reproduce themselves, and respond to environmental changes through biochemical processes that channel thermal motion into highly specific biological functions, while simultaneously increasing the entropy of their surroundings according to the second law of thermodynamics. The universe operates as a vast information processing system, where every particle interaction, field fluctuation, and energy transfer contributes to an ongoing computation of physical reality that processes information about position, momentum, energy, and other physical quantities through quantum mechanical operations that occur continuously throughout space and time, creating a cosmic network of cause and effect relationships that connects every event to every other event through chains of physical interactions. Being requires becoming because existence cannot be separated from process, with every stable structure in the universe maintaining itself through continuous exchange of matter and energy with its environment. From atomic nuclei held together by the constant exchange of virtual gluons, to living organisms that replace every atom in their bodies multiple times throughout their lifespans while preserving the dynamic patterns of organisation that define their identity and function. The poetry of universal motion reveals itself in the profound realization that we are not separate observers studying an external universe, but rather temporary patterns of organised motion through which the cosmos experiences and understands its own eternal dance, with human consciousness representing a particular configuration of matter and energy that has achieved sufficient complexity to contemplate the very processes that created and sustain it. Every thought that passes through your mind, every heartbeat that sustains your life, every breath that provides oxygen for cellular respiration participates in the same fundamental motion that drives stellar nucleosynthesis, powers galactic rotation, and propels cosmic expansion, connecting your individual existence to the grand symphony of motion that began with the Big Bang and continues through every quantum fluctuation, molecular, vibration, and gravitational wave that propagates throughout the cosmos. The recognition that motion is not something the universe does, but something the universe is transforms our understanding of reality from a collection of things that happen to move into a unified field of activity where every apparent object represents a temporary pattern in the eternal flow of energy and information that constitutes the deepest nature of existence itself, making consciousness, life, and intelligence inevitable emergent properties of a universe that achieves self-awareness through the complex motions of its own constituent parts organized into structures capable of reflecting upon the very processes that brought them into being. If this quiet journey through the universe that never rests has brought you even a moment of wonder, your gentle like or soft subscribe would mean everything to me. These cosmic stories find their way to curious minds like yours through your kindness, and I treasure every moment you spend exploring the hidden motions that make existence possible. I'd love to know where in this spinning world you're listening from tonight, and what time it finds you as these words reach your ears. Your thoughts and reflections, whether shared in the comments or held quietly in your heart, become part of the endless conversation between conscious beings trying to understand their place in the cosmic dance. Until we meet again under another sky full of dancing atoms and spinning galaxies, may you find peace in knowing that you are part of the eternal motion that connects quantum vibrations to cosmic expansion, a conscious pattern in the universe's endless dance of becoming. Sleep well, knowing that even in stillness you are moving through space and time as part of the grandest choreography ever performed.